Okay, do you see the slides?
Yes, we do.
Very good, excellent. So, my usual title slide. So, good afternoon, everyone. The pointer. So, where are we? So, 2 weeks ago, before the Easter break, we talked about the beginning of many-body problems. So, second quantization, started talking about elementary excitation in solids, and we saw the example of what are plasma oscillations and how to quantize them. And today we saw also the quantization of the Schrödinger field, so non-relativistic electrons, how we can deal with in a many-body context. And today we're going to talk about how to deal with phonons the same way, so vibrational modes of a crystal. I'll review briefly what we've done, at least from a Lagrangian and Hamiltonian point of view, and canonical quantization, since we dealt with it 2 weeks ago. Next week, I'll probably mention a little bit something about superconductivity, just to make a connection between phonons, electrons, and what else we can expect beyond what we're going to deal with mainly in the rest of the class, which is transport-related issues. So let me remind you a little bit what we did. We saw that in order to properly quantize a system with a finite number of degrees of freedom, we go to a Lagrangian and a Hamiltonian formulation of the classical system. And having done that, particularly in the Hamiltonian formulation, we promote the various dynamical variables, position, momentum, the canonically conjugated momenta to all of the coordinates that we might have. We promote them to operators over a Hilbert space, and that permits us to quantize any particular system. I think at the beginning of the class I said that we know how to quantize an electron because of Schrödinger equation, because of what the matrix formulation that Heisenberg did. But in general, for a general system, we need to have a procedure that we can follow so that we can treat it. We can treat the system from a quantum mechanical point of view. And the case of a system with infinitely many degrees of freedom is typically the first and most important example that we find, in which we need a canonical procedure which is well defined in order to quantize it. So for dealing with elementary excitation in crystal, I told you that actually we have to change completely our perspective on how we view reality. Might be a term a little bit too big, but how we view a physical system, rather than starting from particles as the building blocks for what we do. Instead, we consider fields. Fields are, if you want, a field is a canonical coordinate that is labeled by a position, which takes the place of the discrete index that we have when we deal with, for example, the 3 coordinates x, y, and z of a particle in 3 dimensions. So we need a different procedure, because now we have this infinitely many, actually continuum of degrees of freedom. I gave you the example of the violin string, which can be viewed as a displacement phi labeled by the position along the length of the string. And what we have to do is we have to define something which we call a Lagrangian density, which will be the kinetic energy minus the potential energy of the string at a particular position, if we integrate, which is equivalent to summing over all degrees of freedom. If we integrate this Lagrangian density, we have a Lagrange function, and then we impose the condition that the classical motion of the violin string will be such that the displacement phi at a position x and time t evolves in time in such a way that the integral of the Lagrangian from one particular initial time to a final time in which we assign some specific initial and final conditions, the trajectory, so to speak, so phi of x and t, maximizes or minimizes, so it's an extreme point for the integral of this Lagrangian over time, which is called the action, as it's called also in conventional quantum mechanics. Such a variational problem means that the field phi has to obey as a function of position and time in particular, that gives us the dynamics, obeys a generalization of the Euler-Lagrange equation. Actually, at the end of this chart, this slide, you see something which is formally equivalent to the Euler-Lagrange equations that we saw for conventional quantum mechanics, with some complications. Since x now is a continuous variable, there will be derivatives with respect to this coordinate, so things are a little more complicated, but essentially what we have is, if we define as the functional derivative of the Lagrange with respect to a field as the derivative with respect to the field, but also its derivative with respect to the gradients, so to speak, of the field with respect to the position, summed over the three coordinates if we are in 3 dimensions, then we recover something which is very similar to the Euler-Lagrange equation. So essentially this is an extension, I hope quite, I mean, it may be cumbersome from a calculus point of view, from the notational point of view, but it's just a generalization of the general Euler equations for a variational principle, and we call them Euler-Lagrange because we apply them to the Lagrangian. So the same Lagrange principle that we used to find the dynamics of a classical system with a finite number of degrees of freedom applies to a system in which the number of degrees of freedom is a continuum. Having done that, we define, again, in full analogy with what we did for classical mechanics of a system with a finite number of degrees of freedom. Should be a word to describe this concept, too many words. We defined canonically conjugated momenta density, which is the functional derivative of the Lagrange with respect to the time derivative of the field. It's the same as we saw for classical mechanics, in which a momentum which is canonically conjugated to the coordinate x, for example, is the derivative of the Lagrange with respect to x dot. So exactly the same thing. This is so we can define a Hamiltonian density. In a conventional situation, we have the sum over the p q dot, so the momenta and the time derivatives of the associated coordinates minus the Lagrangian. This is a Legendre transform, which implies that now this function is a functional only of pi and phi, not of phi dot anymore. And we define a total Hamiltonian as we did for the Lagrangian density, in which we have to integrate it over the entire position here. We have to integrate it over space. So this is the cumbersome, if you wish, but I think conceptually simple extension of what we saw for Lagrangian Hamiltonian classical mechanics applied to fields. We can continue generalizing, following exactly the same procedure, see that actually the Euler-Lagrange equation become Hamilton equation when we change variables, and rather than phi and its time derivative, we consider phi and pi. We see that the time evolution of the canonically conjugated momentum density, just a functional derivative of the Hamiltonian with respect to phi, which is the same as p dot equals minus the derivative of Hamiltonian with respect to q, and similarly for the time evolution of the field. So in general, we can also define Poisson brackets, exactly the same. A Poisson bracket between two dynamical variables, the observables a and b, which are functional of the p and q, was defined as the product of the derivative with respect to the p and q and then swapped. Here we have to integrate over space because of the continuous number of degrees of freedom that we have. Essentially r, the coordinate, replaces the index I that we had previously. So as you can imagine, everything essentially is translated from what we saw on the Hamiltonian formulation of a system with a finite number of degrees of freedom, except that now everything is a little more complicated because we're talking about densities and we have to integrate over the spatial coordinates rather than summing over the number of degrees of freedom, the 3 dimensions, for example. How do we quantize this thing? We start by noticing what I stress, and I'll continue stressing the importance of this canonical Poisson brackets that will become canonical commutation rules, that as the P and the Q have a Poisson bracket which gives you 1, while all the P's and all the Q's give you 0, the Poisson bracket between the field and its canonical and a canonical conjugated momentum with respect to a field I, they give you a 0 Poisson bracket unless you take the Poisson bracket between a field and its own canonically conjugated momentum density. And then you get something which is, rather than a Kronecker delta now, you have a delta phi Dirac delta function because of the continuous nature of the index R that we have. And the other Poisson brackets vanish. So we're ready to quantize, following exactly the same thing. Phi, pi, H, the Hamiltonian, they become my operator over some particular Hilbert space. And the advantage that we gain in doing that is that the number of particles that we can consider can change. It's not fixed anymore, which I told you was one of the reasons why people had to think about this extended formulation. And in our case, it would be important because elementary excitation in a crystal clearly can be excited, so it can be created, so to speak, if you view them as quasi-particles. So what we do, everything is now promoted to operators over a Hilbert space, and this canonical Poisson bracket, now they become canonical commutators. And so these are the canonical commutation rules. Again, I will stress the importance of these. These essentially normalize the fields that we have. The commutator between phi and pi has to be equal to dimension h bar. So this sets the scale for the problem, and it is what will allow us to look, for example, at what is the potential associated to a plasmon, the electric field associated to a photon, the ionic displacement associated to a single photon, and so on. So it sets the scale, and it is important for us because this will set the, if you want, the perturbation to the electron transport that any elementary excitation causes on the electron wave functions, and will determine the scattering probability, and so the conductivity, mobility, and so on of the crystal. Okay. The equation of motion will become simply the extension of this equation of motion that I wrote here, the Hamilton equation of motion, except that whenever you have a curly bracket, which is the Poisson bracket, you have 1 over IH bar, the commutator. So that's what we did. And we quantized, we looked at the Schrödinger field. So we found the Lagrangian, which gives us the Schrödinger equation when we take the Euler-Lagrange equation. We define a Hamiltonian density, Hamiltonian, and then we quantize that field. For the electrons, we had to do something a little bit different. These we saw had to be considered as canonical anti-commutation rules. And that's because out of that, first of all, this is demanded by the spin statistics theorem that says that fields which are associated with particles with half integer spin have to obey canonical anti-commutation rules. Otherwise, you violate some, I would say, some sanity checks that your theory has to satisfy, which are the Weitmann axioms, locality, causality, relativistic covariance is not something that we worry about here, but in general one should. So it's a general theorem that tells you that you have to do that. And as a consequence, you get, let's say for free, the fact that Pauli's principle. And I show you that you cannot put more than 2 electrons in a single state. So we quantize that, we quantize the plasmons, the plasma excitations, which are instead excitation of a plasma in which you have a background of positive charges and electrons that can move. Whenever you change the density, the electron density at a given point, you see that the system can be represented as waves, plasma waves, that propagate in a medium, and you can quantize them using canonical quantization. These are spinless objects, therefore they obey the canonical commutation rules, and we saw how to quantize them. And in both cases, we saw that the Hamiltonian can be written at the end by taking the Fourier components of the fields as a collection of harmonic oscillator. Each harmonic oscillator being labeled by the wave vector of the electrons or the plasmons, in the case of a constant potential or zero potential for electrons. And rather than saying that the electrons are your building blocks, your basic building blocks of your intuitive representation of the system, now the field becomes the original building block. And electrons are seen as excitations of these harmonic oscillators. One harmonic oscillator characterized by a particular wave vector can be in a ground state, which means no electrons, or can have one electron or two if we count also for spin. Similarly for plasmons. So now we're going to find the same thing for phonons. Phonons are also bosons. They don't carry spin. Excuse me. So let's go back to something we did several weeks ago. We wrote the total Hamiltonian of a crystal in its glorious form. Quite scary, actually. I remind you what we did. We consider the kinetic energy of the electrons. Each electron is labeled by an index I. Their Coulomb interaction, in this case a Coulomb repulsion. Then we consider the same objects for the ions. So the kinetic energy of each ion labeled by an index alpha. And then the ion-ion interaction. That, of course, is complicated because in principle it's screened. We'll talk about screening by the presence of the electrons, and then an interaction between the electrons and the ions. This is a complicated system, and if you recall, we started by decoupling the electrons from the ions by using the Born-Oppenheimer approximation or the adiabatic approximation, saying, well, the ions move so sluggishly, so slowly, compared to the high frequency at which the electrons move around, that in dealing with the electrons, we can ignore the fact that the ions move at first, consider the ions at their equilibrium position, as defined by the forces that keep the ions at some equilibrium position in a crystal, and then look at the first, second, and third term, and consider this the electronic Hamiltonian. And we went from there and we started dealing with the Slater determinant, single electron approximations, pseudo potentials, and whatnot. And we said, well, we'll worry about this later. So that's this is where now the later comes now. And we have to deal with the ionic Hamiltonian. So what we'll do is, in this section of the class, now we will consider the situation in which actually the ionic coordinates move. They are free to move, essentially they're thermally excited. After quantization, we'll see that this is amounts to a thermal excitation of the harmonic oscillators associated with the second quantized version of this Hamiltonian. And later on, we will go back and look at the electron-ion interaction and see what happens when we remove the approximation that we made in which this ionic coordinates R sub alpha is its equilibrium position, and consider a leading term in a Taylor expansion of this potential around the equilibrium position, the harmonic approximation that we'll make use of also now. So that's what we did. So we separated the electron Hamiltonian, the ionic Hamiltonian, and then what we're going to do now is to do what is obvious. We will be dealing with elementary excitations which are they are states of the system which are not too far away from the ground state. So if you want the leading term, the linear term in a perturbation away from the ground state. So we shall assume that the ions do not move too far away from their equilibrium position. Of course, at some point, if we increase the temperature of the lattice sufficiently, the ions will begin to move around and we get a liquid when the crystal melts. So we will not go as far as considering deviations from equilibrium position, which is more than a few percent from the interionic distance. So what we'll do is we'll take this interionic potential that expresses the interaction, say, gallium arsenide between the gallium and the arsenic, and the gallium in one cell to the gallium in the other cell, and so on. So this interionic potential will express it as a Taylor expansion of what is the value of this potential energy when the ions are at equilibrium clearly summed over all of the ions, this will be just the binding energy of the crystal. It what keeps the crystals together. I remind you that this U is just the Coulomb repulsion between the ions, of course. Otherwise, the crystal will not be stable. This accounts also in some complicated way, and DFT told us how that works, accounts also for the fact that we have electron and we have, of course, the formation of bonds between the ions. So this is an attractive potential. That's the core, which is repulsive, but then we have the attractive potential caused by the chemical bonding or the metallic bonding if you're dealing with metals in the crystal. So summed over all of the ions, this will be just the binding energy of the crystal. There should be a first order term proportional to the displacement U. U sub alpha is the displacement of the ion alpha from its equilibrium position R0. So it's R alpha minus R0 alpha. This is this variable here. Of course, there should be a first order term. However, if we sum, so this is approximately correct here. If we sum over all of the ions, all of the, for a particular ion alpha, if we sum over all of the other ions beta, this first order terms, the sum of these first order terms represents the sum of the forces that are acting on that ion. Since we're dealing with an expansion away from equilibrium, clearly the forces, the sum of the forces acting on the atom at equilibrium is zero. And that's why there's no first order term here. We do have a second order term, which is what we call the harmonic term, because it's proportional to the displacement, the square of the displacement, if you wish, like in the potential of a harmonic oscillator. And of course, there will be a plus dot dot dot, which is higher order terms that are important, of course, as U gets bigger. So as we approach the melting point of the crystal, this becomes more important. It's also extremely important for example, heat conduction, because this anharmonic term represent interactions among phonons themselves. But for now, we shall ignore them. Actually, we shall ignore them for the rest of the class. I will never deal with them anymore. So what we have is essentially that this ionic Hamiltonian now, if we consider the fact that the sum over all these U's and the forces is zero, and this is just the binding energy of the crystal that we can set to zero as the reference energy of our system, what we can write for the lattice Hamiltonian is just the kinetic energy of the ions. And then there will be just this term over here, which is the remnant of our expansion. This is just this matrix here, which is, by the way, the extra 1/2 comes from the fact that we don't have to, this 1/2 over here, so there's 1/2 from the fact that we don't have to double count each pair, and this is just from the expansion, the Taylor expansion. So this is called the dynamical matrix or dynamic matrix, and it's the crucial element, the crucial ingredient that we have here. I will stop here for now in terms of the general formulation. I would like to go to simpler cases. I will look at the linear chains, two linear chains, a monoatomic chain and a diatomic chain that we will need later on dealing with a dielectric screening to deal with the screening by the ions. And the idea is that this problem appears to be daunting exactly the same way the problem of studying the electronic states seem to be daunting, simply because of the sheer number of electrons and of ions that we have here. Of course, the important ingredient that simplifies the problem and makes it solvable is the fact that the system is periodic. So we will have to use periodicity in order to simplify this problem. If we write this in some matrix form by discretizing, clearly this would be a matrix which would be of infinite rank. And even if we chop it, we don't know exactly where to chop it. So we will have to use periodicity, and this exactly as the problem of studying the electronic excitation in a crystal can be reduced to studying everything in a single cell, or in a single cell in K-space, which is the Brillouin zone. Similarly, what we'll have here is we will be able to reduce the rank of the problem from infinite, which is what we have now, to a much smaller rank, essentially the number of ions that we have in a unit cell, exactly as we did for electrons, going to the unit cell, times the dimensions of the problem. So if we have 2 ions per unit cell, we'll be able to reduce this problem to a 6x6 eigenvalue problem, which is something we can deal with. So I want to show you by looking at the monotonic and then the diatonic linear chains where the periodicity comes in and how we can simplify the problem. So here I had this picture which is a diatonic chain. Let me assume that we're dealing with a monotonic chain, which means that the red ions with labeled with a small mass m actually are identical to the black ions with a big mass m. So the same ions everywhere. So the periodicity of the lattice now is simply A. This is really monotonic and linear, which means we're dealing with one dimension only. We will assume that the ions can move only on the horizontal plane and not out of the plane or vertically. That will happen in 3 dimensions, and I will discuss it later. So let's take the problem as simple as we can. If we write this problem, this equation now for our chain, we can replace the indices alpha and beta, which label the ions, simply by the position L in which we're dealing with the ions in a cell. So the position of the ion will be A times an integer. This integer is called L. And we assume that 2 ions can interact via some dynamic matrix, dLl prime. This is the second order derivative, this object over here, of the interionic potential between an ion at position L and an ion at position L prime somewhere else. And this is proportional to the displacement of the 2 ions at L and L prime. By translation symmetry, we see that as long as L minus prime, the difference between L and prime is fixed, you have the same distance between the ions. So by translational symmetry, we can represent this matrix simply by dl and L prime and 0. And also the sum over L of this dynamic matrix, the same argument that I gave you before, has to be 0 because this represents equal shift for the ions, all the ions in a crystal. So now, having written the Hamiltonian, we can write the Hamilton equation of motion, the time derivative of the momentum, canonically conjugated to the coordinate r sub L, which will be just mv, the velocity of the ion L, will be equal to this expression. It's the sum of the forces, if you wish, and this is the kinetic energy term, written in terms of the kinetic energy term. Okay, so we can write this equation now. In this equation, we can write it explicitly, having used this formula, and we will also assume that the interaction is nearest neighbors, which means that dl and L prime is different from 0 only when L and L prime differ by 1, plus or minus 1. As you can imagine, if I had to deal with interactions at longer distances, it will get a little complicated. But we'll simplify the problem. Let's assume that only nearest neighbor interaction is present. So now our equation of motion becomes relatively simple. The acceleration of a particular ion L is given by the force of the ion preceding it, following it, and then there might be some term which is proportional to the some on-site interaction of the ion with itself, and we can set it equals to 0 if we wish. And let's simply label, I think I labeled D somewhere here, down here, simple label D, the only non-zero element that we have for the dynamic matrix, which is the spring constant, if you wish, of this spring over here. It's the same for everybody, so let's just call it D. So now we can write this equation of motion in some simple term in this particular fashion. Again, now this is a system of infinitely many equations, one for each L. The acceleration of the ion L is given by the push of the ions left and right, push and pull. And that's where we simplify the problem. By periodicity, we know that the displacement of the ion, essentially it's Bloch theorem, but now applied to ions, has to be equal to, okay, there will be some time dependence which we can always decompose into its Fourier components, so we'll consider one component omega, and then there will be a dependence on position, which is given by this trigonometric expression, if you wish, and let's call it a polarization vector, the displacement, the basic displacement. And the important thing is that this object does not depend on L because of the periodicity of the system. And this is what simplifies the problem. If we now plug this expression into our equations of motion, we get essentially simply a secular equation, so to speak. The second derivative will give us just minus m omega squared. Second derivative here, this is the m, this is the minus omega squared, and I've already divided by dr. And then we have the form that we get from the forces that we have. And we see that essentially we have reduced the problem of an infinite set of linear equations, coupled equations, to a single cell, if you wish, in which we have immediately a relationship between omega and the q vector, the wave number of the propagating wave. Okay, this is not clear why I call it a secular equation. It will be apparent in the next example, which is the diatomic chain, in which indeed we will have a matrix expression for our problem. It will be a linear problem, an eigenvalue problem, or a homogeneous linear problem that admits a non-trivial solution only when the determinant of the coefficients is 0, which is the secular equation. So this is the simplest example that I can think of. Notice that we get for any wavelength or any wave number, the wavelength will be just 2 pi over q. For every wavelength of the oscillation, we get a particular frequency. So this is a relationship between the frequency of the oscillation. Again, this will be, this will be an oscillation of ions which move left and right, and for any wavelength, there is a particular frequency in which they move. And this frequency essentially starts linearly with q. By expanding the sine function, we get some linear dependence. And then at the edge of the Brillouin zone, it is reached with 0 slope, and there is some particular value of the frequency. So it's a sinusoidal function. I start from 0 in a linear fashion, and then it reaches the edge of the Brillouin zone 2 pi over a. Okay, let's extend this problem to a diatomic chain. It will be a little bit clearer why I call this equation the secular equation, because it will be immediately apparent that we have to solve a homogeneous system. So now we have the same picture that I had before, but now these red ions are considered to be some lighter ions, and these are heavier ions with a mass m. So now the primitive translation distance vector, it's in one dimension, so distance is 2a, because the cell is twice as large. And then we can write the problem now in terms of the displacement of the ions. And let me call 1 the big ions, and with the subset 2 the displacement of the little ions, the red ions. And that's why we have different masses. And we can see that the acceleration of an ion, a heavy ion, 1, is given essentially by the push and pull that the lighter ions preceding and following give to this ion itself. And the same situation happens for this guy. So there will be 2 terms. One is a push and one is a pull from the left or from the right. Again, we can use periodicity. We have to use periodicity. This is a infinite system, of course, of coupled linear equations. Remember that now, so we use exactly the same expression that I had, where did I have it? My apology. The same one, except that now the periodicity of the cell is 2a, so there is a 2 because of the definition of the constant a that I gave here. And again, the same exponential dependence on time and the same complex exponential dependence. And then these parameters v1 and v2, which are the, if you want, the polarization vectors. If we were in 3D, these are simple numbers, but these are the basic displacements of the ions, which is modulated as you go along the line. and it has to depend, the dependence on the position appears only in this exponential term and not in V1 and V2 because of the periodicity of the system. So we plug this back into these equations and we get a couple of equations linearly coupled. These are equations in V1 and V2. It's a linear system, homogeneous. We can rewrite it in explicit homogeneous form. And we know that a homogeneous system, linear system, admits a non-zero, non-trivial solution, which means, of course, there is a solution V1 is equal V2 equals 0. That's a trivial one. We're not interested in that. There will be a non-trivial solution only when the determinant of the coefficients is equal to 0. And the determinant of the coefficients will be this object here times this, which I wrote here, minus the product of the two off-diagonal terms, which is this square and then 1 plus the exponential of plus and 1 exponential of e to the minus, which we have written here. So this is an equation which is a second degree in omega square. So we can solve it in terms of omega square. This is the standard solution of the second degree algebraic equation that we have. And we have two different solutions. It's interesting to look at what is the form of the solution when this parameter q goes to 0, wave vector goes to 0, and what happens when q approaches the edge of the Brillouin zone that now is pi over a because of the fact that a is just a half of the length of the primitive cell, so to speak. So we see that we have two solutions. Of course, it's we can have a plus or minus, and these two solutions, let's call them omega plus and omega minus. The high energy, high frequency solution starts off at q equals 0 with this particular value, which is twice the spring constant that we have assumed, multiplied by the inverse or divided by the reduced mass, if you wish, of the system. As you move along the Brillouin zone, along Q, towards the edge of the Brillouin zone as this pi divided by 2a, we reach a value which is 2d divided by the mass of the lighter ions. The other branch, the omega minus solution, has a very different behavior. It has the same behavior that we saw for the monatomic chain, essentially. It starts off almost linearly with a slope which is given by the square root of this number, and then it approaches the edge of the Brillouin zone, the one-dimensional Brillouin zone, with a frequency which is the square root of twice the spring constant divided by the mass of the heavy ions. These are called optical and acoustic branch. The name comes from this. If you go and look at V1 and V2, what are the solutions of our problem? When we're dealing with the omega minus, when we plug omega minus here, we see that V1 and V2 have the same sign for all Qs, which means that the two ions in my plot here, the big M and the little m, move by different amounts as we move along here, but in the same direction, move in phase. So essentially what this represents is the propagation of an acoustic wave. Even if these ions have different charges, if this were an ionic crystal, say gallium and arsenide in one dimension, gallium and arsenic, so that there is some electron transfer between the gallium and the arsenic, and these are actually positively or negatively charged. In this case, there is no dipole or dipole field associated with that, which is formed in a single cell because the two ions move in phase. And that's why they're purely acoustic waves. On the contrary, if we go and look at what V1 and V2 are, our solution of the system, when we plug for omega plus, we see that V1 and V2 have opposite signs. This means that the two ions, big M and little m, move out of phase, one against each other. And this results in a dipole, if these were charged. And this, of course, creates a dipole field, and this can couple to light. and that's why they're called optical. So the optical branch is usually it's a higher energy because there is the Coulomb interaction between the ions that increases the frequency. It makes it stiffer rather than the acoustic, which is much weaker. And it is at high frequency throughout the entire Brillouin zone. Notice that the acoustic branch has to have a frequency that goes to 0 when the wavelength goes to infinity, as Q goes to 0, and that's because for an infinite wavelength, so if we increase the wavelength, the translation of the two ions is the same in each cell. For a fixed wavelength, there will be a different distance between the two ions in the next cell and different yet in a third one. As the wavelength increases and goes to infinity, the distance, the displacement between the two ions in each cell is the same. So essentially what this is just an adiabatic shift, translation of the entire lattice. So there's no change in the energy that we need to for the crystal when we have an acoustic wave of infinitely long wavelengths. That's why the frequency goes to 0, because nothing happens essentially. As the frequency increases, as the wavelength decreases, then we begin to have some different interaction between the ions because the distance between the two ions in each cell changes from one cell to the other, and then the energy associated with the mode of its frequency increases, and it gets stiffer as we go to the edge of the Brillouin zone. By the way, the fact that at the edge of the Brillouin zone you reach the dispersion has 0 slope, it's a general property that we also saw for electrons. Okay, so this is the particular case. Now we have to go back to where we were before, which is what are we going to do with this equation. So in this particular in the particular cases that we saw, we were dealing with only one dimension. The dynamic matrix was assumed to be a spring constant, so just a constant independent of anything else. So now we have to go back and look at a general case. So the first thing that we have is that in a general case, we are in 3 dimensions. So things will be a little bit different from what the oversimplified pictures that I gave show. And so we have essentially a bunch of families of phonons. We saw already the difference between the acoustic and the optical phonons. So acoustic phonons are essentially what I showed here, what we saw before, longitudinal waves in a one-dimensional chain that we saw here. We can only have a displacement that propagates along the direction of propagation. So they're longitudinal by definition. But in 3 dimensions, you can actually have 2 situations. Let's consider a cell in which we have the red ion and the blue ion. The distance between the 2 ions can change. Here it's big, then it gets smaller and smaller, bigger again, something bigger, smaller again. So there is a sinusoidal change of the distance between the 2 ions, but the 2 ions themselves do not move with respect to each other. And you see that the change in the distance occurs along the direction of propagation. If you want, the displacement vector or the polarization vector of each ion is along parallel with the propagation vector, the k vector. So the displacement is parallel to k. You can have a different situation in which, again, the ions in a cell do not move with respect to each other, but their distance changes from cell to cell. And you see that now we have a displacement which is perpendicular to the propagation vector, to the k vector. So these will be called transverse waves, and this will be called longitudinal waves. For optical vibrational modes, you have the same situation. You can have longitudinal waves, in which now it is the distance between the 2 ions in a cell that changes. Here is 0, here is a positive value, then it goes negative, and so on. So there is a displacement of the ion along the longitudinal direction, along this direction, of the red ion and of the blue ion, which are out of phase. Okay. But the displacement is, again, as it was in this particular case for acoustic phonons, the displacement is along the propagation direction. And these are optical longitudinal phonons. And finally, you can have transverse phonons, optical phonons, in which now the displacement of the ion is out of phase, again, as it was here, but the displacement vector, the polarization vector, if you wish, is perpendicular to the propagation direction. In this case, the red ions moves this way. In this case, the red ions move this way in a perpendicular direction. This is quite important because we will see, for example, that when you have optical phonons, electrons can interact only with the longitudinal modes. This is a general property which can be derived from, after we will have dealt with the dielectric function of the material. Transverse phonons actually couple to light because light is a transverse wave. Longitudinal optical phonons do not couple to light. So in general, things are, I'm oversimplifying a little bit, assuming that, for example, the distinction between longitudinal and transverse can be done uniquely and always. We'll mention it a little bit later. The same for acoustic and optic. Actually, when you go towards the edge of the Brillouin zone, things get very complicated. And actually, it's at the very edge of the Brillouin zone, it doesn't even make any sense to distinguish between acoustic and optical modes. And transverse and longitudinal also, they begin to be mixed as soon as you move away from a high symmetry point, like the center of the Brillouin zone. But it's useful to keep this distinction in mind. So not only we have two different families, but now in 3 dimensions, we will have a bunch of modes. Also, you realize that for acoustic modes, if I were to plot here a situation in which I have 3 ions in a cell, for acoustic modes, there's very little I can do. This group of 3 ions keep moving synchronously in phase. All the 3 ions move in phase along either the propagation direction or in a perpendicular direction. So we will always have 3 acoustic branches, a longitudinal one and the 2 transverse. Clearly in 3 dimensions you have motion, a transverse direction, not only on the plane of the slide, but also out of plane. So you will have 1 longitudinal mode and 2 transverse modes. For optical phonons, if I add another ion here, you see that things get more complicated because now the ions move out of phase with respect to each other. But if we have 2 ions, there's only 2 ways they can move out of phase. If we have 3 ions, there are many more ways. And for complicated cells that we have in some materials, you can have different groups of relative motions of one ion with respect to the other one. So the number of optical modes is larger. In general, if you have n ions in a unit cell, you will have 3 acoustic modes, the 2 longitudinal and the 2 transverse and the longitudinal, and then you will have 3 n-1, 3 open parentheses -1 and -1 optical modes. So if you have only 2 ions per cell, as is the example that I depict here, there will be 3 optical and 3 acoustic modes. If you have 3 ions in a unit cell, you will have 3 acoustics and 6 optical modes, and so on. So the number of optical modes is larger, usually it's complicated, and sorting them out in terms of understanding how the ions move with respect to one another, in general, it can be quite difficult. So I hope that this is clear. Let me stop a moment, and if you have any questions, please ask. As usual, I beg for questions. Am I still online, by the way? My usual question that I have to ask periodically, do I exist? Yes?
You do.
I do. Yeah, I'm asking because also in the last week, my Wi-Fi has been very erratic. The cable company went down several times, so I was afraid of losing connection. Good. Okay, so let's go back to the general theoretical formulation of what we have to do. So this is the same ionic Hamiltonian that I wrote before. The dynamical matrix is this object here, except for a 1/2 factor that I haven't written. Well, I've lumped it over here outside. So this is the dynamical matrix. I've written it explicitly. Now, rather than a single label alpha for the ion, what I'm doing is I'm going back to the notation that we were using before. I will use the Greek letters, the beginning of the Greek alpha, beta, gamma, for the ions in each cell. So this is a number that can run only over 1, 2, 3, small number, whatever is the number of ions that you have in a cell. And I will use the index L to label the cell. Clearly, this index L will be a set of 3 indices if you want the 3 indices of the translation vectors along the 3 directions. So the momentum conjugated to the position of the ion RL gamma will be given by m gamma times the time derivative and the usual momentum. And m gamma is the mass of the ion. Clearly, the mass of the ion does not depend on the cell because of the periodicity. So we can rewrite the total Hamiltonian, the kinetic energy. We're summing over all of the ions L and gamma, all of the cells and all of the ions in each cell. The 1/2 here comes from the usual expression for the kinetic energy, and here it's simply because of the Taylor expansion that we used to express the interionic potential only in terms of its leading term, the first non-trivial term, which is the second order. And then, of course, we have to sum. I apologize for the many indices. Of course, the displacement of the ion in cell L and ion gamma, of course, it's a vector, so it will also have x, y, and z coordinates, components, and I write them as I and j. So I and j run over 1, 2, 3, or x, y, z. I know it's a little awkward. Well, let's simplify it right away. So we use now the general expression that we introduced here somewhere, here, for example, okay, using periodicity, the periodicity of the crystal, to express the displacement, delta R, which here is called U, in terms of a quantity that does not depend on a cell. This is crucial because it's what allows us to look at a problem only in a single cell, and so make it render it from an infinite set of system of linear equations to a system of a few linear equations, 3n, 3 times the number of ions that we have in a cell. So now this is exactly the same thing except for a normalization. I'm dividing by the mass of the crystal, if you want, the total number of cells that we have in a crystal and total mass of the cell. This is for convenience, so that I can get rid and reformulate the Hamiltonian in terms of the sum of Hamiltonians of harmonic oscillators. That, of course, is what I'm driving at. Then we have the usual dependence on time. I'm looking at one coordinate, one component, Fourier component at the time. And then I have the dependence on position, which is by Bloch theorem, essentially, can have only an expression of this sort. This guy, which is the polarization vector, well, it's related to the polarization vector, can depend on Q, of course, on the wave vector, so the wavelength that I have. It depends on which ion in the cell I'm considering, but again, the important thing is that this guy does not depend on L. Otherwise, I wouldn't be able to solve anything. So the only dependence that I have is this, if you want, the Fourier dependence, which is caused by symmetry. So this is the crucial ingredient that permits me to simplify the problem. Okay, so now what we're going to do is take what sometimes we can call the lattice Fourier transform of this mess over here. We saw before, for example, let me go back here where I talked about something like that, or something like that, this relationship. These are general relationships that depend on the symmetry of the translational symmetry of the system. Probably this would be the important relationship, okay? So since this dynamic matrix depends only on the distance between the two ions, not on the absolute positions of them, but only on the difference between the two positions, I can take a Fourier transform of this object over here with respect to this difference. Then this object will not depend on two set of cells, but only on one, which is the difference between, if you want, L double prime is the translation vector that corresponds to R sub L minus R sub L prime, okay, which I can define by translation symmetry or the periodicity of the system. If the system were not periodic, if I didn't have a crystal to deal with all its symmetry properties and translation properties, I wouldn't be able to simplify the problem in this way. So now this dynamic matrix depends only on, of course, x and y. It's three components because we're in 3 dimensions. On the number of ions that we have, it's a matrix, so there is an index that depends on the ions. So it's a 3n by 3n matrix, where n is the number of ions in a single cell. That's important. So it's a small number, and it's given by this. Now I can take, I can express this in terms of a Fourier components, and each one at a time, and I see that I can rephrase, having used this property here, that again I can do. This does not depend on L double prime. It only depends over here on the Fourier components because of the symmetry of the problem, the translation properties of the problem. Then I see that I have reduced my problem, which is daunting over here, lots of ions, lots of cells, lots of ions in each cell, only to a problem which has a rank, which is, as I said, 3n, 3 times the number of ions that I have. The 3 is because I'm in 3 dimensions, so di and j over here, and dn is the number of ions in each unit cell. This is a linear system, and I've written here already the secular equation, if you wish. It's implicit over here. This is a linear system for the polarization vector psi for a given wave vector, a given ion, and of course x, y, z. And this is a linear system, not very long, not very big, as I said, 3n by 3n. And it can have a solution which is non-trivial, so non-zero psi, non-zero displacements, only when the determinant of the coefficients is equal to 0. So setting the determinant of this matrix to 0 will give me a secular equation that admits 3n solutions. I will use the Greek index eta to denote these solutions, which are the eigenmodes of the system. Again, it goes between over 3 acoustic modes, 1 longitudinal and 2 transverse, and 3 anions minus 1 optical modes, which are the, as I told you, the optical phonons that you can have that are more than 3 if we have more than 2 ions in a unit cell. Okay, so we can find the solution of the secular equation. If n is only 1, if we have a monatomic crystal, then probably we can even do it by hand with a diatomic crystal like silicon, like any FCC of the zinc blend or diamond structure. We have 2 ions in a privity cell, so it's a 6 by 6 problem, is a 6-degree equation. We cannot solve it analytically, unfortunately, but we can solve it numerically relatively simply. And what we find is, here I illustrate the solution for silicon. What you see here is the acoustic phonons. There are 2 transverse. You don't see it here in this particular plot along in a symmetry line, and that's because these are symmetry lines, gamma to L and gamma to X. But if you go along some strange direction, then you see that actually you have 2 modes. They happen to be degenerate only along the symmetry lines. And then the longitudinal. My clock, 10 o'clock. Okay. And then you have, similarly, since it's silicon, since we have 2 ions in unit cell, we're going to have also 3 optical phonons, 2 transverse, and you see indeed that as it happened for the acoustic phonons, you have a splitting of this degenerate, doubly degenerate line when you go along a general direction, and 1 longitudinal mode. And there is some crossing. Now, here I'm plotting the phonons going from the center of the zone to the edge of the zone. As I mentioned before, the distinction between transverse and longitudinal, it's quite clear. At gamma, at this particular point, actually is perfect. If you do the calculations, and now there are computer packages which have become of practically routine use. If you use the DFT package VASP, there is the add-on program PhonoPy, which lets you calculate the phonon dispersion quantum espresso also lets you calculate the phonon dispersion. And if you go and look at the polarization vectors, these objects, this psi, which are vectors, along gamma, you see indeed that you can distinguish transverse and longitudinal phonons very clearly, and acoustic and optical. You see that the displacement is exactly parallel to the Q vector when you're very close to the gamma point, and the polarization vectors of various ions in a cell are in phase for acoustic phonons and out of phase for the optical phonons. Here, I'm really at the edge of the Brillouin zone. I'm moving along the edge of the Brillouin zone from the point X, which is at the center of the little square that you have in a Brillouin zone, to a corner of that square, to the point kappa, or k, big K rather than kappa. Here, the distinction between acoustic and optical, longitudinal and transverse gets iffy, in particular because transverse and longitudinal already midway between gamma and X, you see there is some significant mixing. So general rules that you will read, and I will mention later on, electrons interact only with longitudinal acoustic phonons, electrons interact only with longitudinal optical phonons. They do not interact with transverse modes. These are half-truths. Ideally, only near gamma. As soon as you go away from gamma, then these modes get mixed, and then you have interactions also between electrons and transverse modes. And here also, distinguishing between optical and acoustic, it's impossible. So if I had to decide how to color, for example, a plot and see, is this acoustic or this optical over here, I wouldn't know how to do it. Indeed, you see that the displacement vectors are neither perfectly out of phase nor perfectly in phase for any of these modes. It doesn't make any sense. You realize that when I got to wavelengths which are so short that I begin to enter wavelengths which are shorter than a single cell, saying that the two ions move in phase doesn't mean anything anymore, because they actually will begin to move out of phase even for acoustic modes. I hope it's clear. Otherwise, try and visualize it and convince yourself that indeed it doesn't make any sense to call optical acoustic transverse longitudinal where you are very close or even at the edge of the Brillouin zone. These are the general properties, though, that you see for many materials. The acoustic phonons have, as I said, linear dispersion, usually always. The transverse slope of the transverse modes is smaller than the longitudinal modes. The slope is actually the sound velocity. So you can define a transverse and a longitudinal sound velocity. And typically, we will see later on, you can approximate the dispersion of phonons that enter transport of electrons which are not too far away from the bottom of the conduction band. So dealing with the mobility, for example, they cannot exchange very large momenta, not large Q. So you can approximate these as linear dispersions, in which the frequency of the phonon is just the Q vector, the magnitude of the Q vector times the longitudinal or the transverse velocity. Optical phonons are often approximated by a dispersionless, a single number, some 60 millivolts, for example, for silicon. Notice that the frequency, as we saw here, somewhere, where was I, in the plot, the frequency is inversely proportional to the mass, the square root of the mass. So for lighter materials like carbon, this energy is much higher. The frequencies are much higher. For graphene, for example, the energy of the optical phonons hovers around 200 MeV, so it's a factor of more than 3 higher than silicon. For germanium, this will be on the order of 40 millivolts and so on. For gallium arsenide, which is heavier yet, it's about 36 millielectron volts at gamma. So the general properties are illustrated here for most of the FCC crystals that we'll deal with, which are 2 atoms per unit cell. This is the typical plot that you have. Just rescale the energy scale or the frequency scale depending on the mass of the cell that you have. The heavier the mass, the lower the frequency, and vice versa. Okay, so now we have a classical description. Remember, this is a classical description of our phons, of our vibrational degrees of freedom of the crystal. We have formulated in terms of Hamiltonian. You may complain, well, actually you didn't define a Lagrangian density and so on. It's true. It was very convenient to use this expression. Actually, if I had to define a Lagrangian density, I would simply put a minus over here. I would get the same thing, and I would express, rather than P, R dot, I would use this expression and use the R dot, and that would be my Lagrangian. It's not really a density, it's a discrete thing, but still the number of degrees of freedom is infinite. Again, it was crucial, and I remind you, to make use of the periodicity of the crystal in order to convert the problem from a linear system of an infinite rank to a system of a finite rank, relatively small. Again, 6 by 6 for most of the materials that we will be dealing with, so relatively small. Now we have to quantize it. So how do we do it? Okay, and let me rewrite this expression here, this one. I will lump this object divided by the mass of the crystal, square root, mass of the crystal. I will separate it into a vector of unit length along the direction of the polarization. I remind you, this is the polarization vector. It tells me for a given Q, how much the ion gamma in a given cell is moving away from its equilibrium position. So this points at the direction, oops, points at the direction. What did I do? I clicked something wrong. Okay, it points in a direction that tells you where the displacement, where the ions moves away from equilibrium position, and the magnitude. So I want to separate the magnitude from its direction. So the unit vector along the direction of this guy, it's called the polarization vector, and I will call it E, little e. Where am I? Here. Okay. And the magnitude, so this is a number, a C number if you want, the magnitude of displacement will be called Q. Since I'm considering the stick to silicon, the 6 modes, eta runs over 3 acoustic and 3 optical modes. So I already consider only the displacements that I get by solving my secular equation, so the eigenmodes of the system. So the displacement, again, does not depend on the cell except via this complex exponential, the wavy nature of the oscillation. And this is the variable that I want to consider as canonical coordinate for my system. So I want to express the system, which is again is a system on infinitely many degrees of freedom, by labeling these degrees of freedom not by the number of the cell number and the ion index, but by the wave vector and the branch, which particular eigenmode of the system I'm considering. So I will use this definition as my definition of the canonical variable, and I will consider its canonically conjugated momentum, which I can write the same way with defining some objects P. And now these are my canonical coordinates, and I quantize the system by requiring the canonical commutation rules between the Q and the P. The names that I've chosen for this variable is obvious because Q is the usual terminology, usual notation for the coordinates in Hamiltonian formulation, and P the momentum. So I will have canonical conjugation rules. They come from the Poisson bracket that actually one can derive by looking back at this Hamiltonian and derive the Poisson bracket. And I promote them to operators over my Fock space that we described last time. Okay, so the Hilbert space, which is associated with this system. So now I can do some manipulations using essentially picking up these guys, these expressions for the dr and the p, plugging them into the expression for the Hamiltonian, and exactly as we did for electrons and plasmons as well, we find that the Hamiltonian, the total Hamiltonian, now an operator over my Fock space, can be written as a collection of, you recognize, harmonic oscillators. So we have a bunch, infinitely many harmonic oscillators, each labeled by its branch index, transverse, longitudinal, optical, acoustic, and the wave vector that we have. So this is exactly what we wanted to achieve. Now we have to do a little bit of algebra to rewrite these operators, P and Q, in terms of essentially Fourier variables, the equivalent to the Fourier coefficient of the Schrödinger field or the Plasmon field that we did in the past, last week, 2 weeks ago, in order to write it in terms of the creation or annihilation operators that are convenient, because we know how to deal with that thanks to Dirac's algebraic solution of the harmonic oscillator. Any questions so far? Okay, so this is my Hamiltonian. This looks like a Hamiltonian harmonic oscillator. This is essentially the same thing that we can write for the harmonic oscillator in conventional quantum mechanics. Better yet, we can do a little bit of a transformation. There's no general rule on how to do it, but once you've seen 1 or 2 cases, you can guess what is the right linear combination of Q and P that you have to use in order to convert your Hamiltonian to this form. So we will refine the displacement operator as this number. This is quite important, actually. Keep it in mind, because this is related to what I keep saying, is the displacement of an ion in centimeters, in axioms, nanometers, whatever you want to express it in. It's the displacement of an ion in the presence of a phonon. So this is something that can be very useful in many situations. And by the way, that will enter also the expression for the electron-phonon interaction. And these are just the B operators, the creation annihilation operators, so that the Hamiltonian, except for the famous 1/2, can be written in terms of the Hamiltonians or harmonic oscillator expressing the Dirac algebraic formulation. And like we saw for electrons, okay, these were anti-commutators for electrons, if you remember. We have similar expression, but now we are commutators for these creation annihilation operators. So the BMB dagger commute, sorry, there should be no dagger. I simply cut and paste this expression. There should be no dagger here, should be a dagger here. My apologies. Let me correct it here if I can write it. Come on. So this is a dagger. There's no dagger here. Okay. All right. So again, this is the important idea. As I told you, it usually what one can do is to define BMB dagger in such a way with an arbitrary coefficient here, yet to be determined, and then you go and impose the canonical quantization rules. They tell you that the commutator of these two guys has to be 1 when Q prime are equal and the prime are equal. So this is, again, what sets the scale of the problem, what tells you what the unit displacement will be. Okay, any questions? I'll do a little bit of a discussion about this in a moment. Before going there, I want to conclude the set of excitations. I was a little bit hesitant on the word I should use, of fields that we should quantize, and then we'll come back to electrons and to phonons, and I want to discuss a little bit what is the again the average displacement that we have caused by a phonon, the presence of a phonon, which is what these canonical commutation rules require, and then I will give you a brief mention of a consequence of this displacement, or the dispersion of the phonons that you have for two-dimensional materials, referring to a theorem which is called the Mermin-Wagner theorem, because it's an interesting application of the second quantization study. Okay, before taking a little break, let me finish up quickly with the quantization of the electromagnetic field. So I talked about quantizing elementary excitations of a crystal. Clearly, these are not elementary excitation of a crystals, but we can use the same machinery, and it's useful to do it. You may recall that I introduced the second quantization issue with two problems that conventional quantum mechanics cannot deal with. One is a number of particles or quasi-particles as excitation that changes. Photons can be emitted, can be absorbed, so their number changes. If you want to deal with a conventional machine, the conventional machinery of quantum mechanics, once you set a Hilbert space for a given number of particles, you can choose any number you want, but once you choose one, you're stuck with it. So instead, you want to deal with a system in which the number of particles of excitations can change. And they use excitations only also to describe electrons or neutrons or muons, excitations of a particular field. That was one reason. The other reason was a little more mundane or prosaic, if you want. If I told you of a hydrogen atom excited with an electron in a 2p state, what will happen? And we know that it decays, but we don't have the machinery. At that point, we didn't have the machinery to deal with it. The electron could not decay. It was in an eigenstate, the stationary eigenstate of the Hamiltonian, so no external perturbation because the ionic potential due to the nucleus was already diagonalized exactly. So the problem was solved exactly. We had an excited state, and that was it. So the decay could be derived either empirically, well, I shouldn't say empirically, but from thermodynamics or detailed balance consideration, which is what Einstein did before quantum mechanics was even invented. I think it was 1916, I don't remember exactly, when he came up with the Einstein coefficients. That accounted for the fact that in order to have equilibrium, you need to have also spontaneous emission, which is sort of a mystery. If you quantize the electromagnetic field, as we're going to do now instead, you see that the electromagnetic field is just always there, even if you don't have any photon around, any electromagnetic field, the field is still there in its ground state, in its vacuum state, so the ground state of the Fock space, but it's still there. And so the coefficient 1 plus n, particularly the 1 for spontaneous emission that you get from for the electron-photon interaction of electrons with electromagnetic field, will come out automatically because it can be viewed as an excitation or resonance with the quantum oscillations, quantum fluctuations of the vacuum. So what do we do here? We want to do exactly the same thing that we've done for the, let's see, how many have we considered now? The Schrödinger field, electrons, plasmons, and phonons. So we're considering already 3 types of fields. This is the 4th type. We want to follow exactly the same route. So let's start with Maxwell equation. Let's make it simple. Let's consider in vacuum. I may post a homework assignment, so to speak, if I haven't done it already, I'm not sure, in which you will be asked to try, again, the homework assignments, but you're welcome to do it, not to do it. I encourage you to work on them. I will post the solutions as well. To derive a Lagrangian density for Maxwell equation in the presence of charges and currents. Now we'll deal with the homogeneous Maxwell equations, free space, no charges, no current densities around. It will be simpler. But again, I'll post a homework assignment so that you can work it out and do your things. See that you can actually derive a Lagrangian whose Euler-Lagrange equations satisfy or are equivalent to Maxwell equation. So we will have to find a Lagrangian density such that the Euler-Lagrange equations give me these 4 equations. So the first thing to do is we know that the total energy of the electromagnetic field is given by the square of the electric field plus the square of the magnetic field. There is a plus if you look at the total energy. Okay, let's be sort of cavalier. Let's consider the electric field as a kinetic energy component and the magnetic field as a potential energy component. Clearly, this doesn't make any sense in the way I said it, but formally, from a mathematical point of view, it's a good starting point. So let's consider the Hamiltonian will be the sum of these two. So the Lagrangian will be, rather than the sum, the difference between the two. And let's introduce immediately, rather than using E and B, let's use the vector potential A and the scalar potential phi. The good thing is that by using this expression for the electric field, we have immediately that we satisfy this equation and this equation, these two. The curl of V will be the curl of B, the curl of a gradient is 0, so we immediately satisfy this equation. And this will give me the curl of B, so the divergence of B will be the divergence of a curl, which is always 0. So we satisfy the Maxwell's equation just by using the proper, what they will become sort of canonical variables for my quantization. So the other two equations, the first one, Poisson equation, Laplace equation, which will become Poisson, and this equation of the curl of B, they can be, they should be derived from the Euler-Lagrange equations for this Lagrangian density. So the algebra is a little cumbersome. I encourage you to do it if you're willing to, and see if you can manipulate this thing such that out of this is the Euler-Lagrange equation by taking the derivative with respect to phi. So this will be the time derivative of the functional derivative with respect to phi dot. Remember that the functional derivative also means that you have to take the derivative with respect to the gradients. So there is this additional term. And then you have this. You see immediately that the Lagrangian density does not depend on phi dot. This will give you immediately the Laplacian of phi, and you're left with a 0. So you recover immediately the first of the Maxwell equation, the first three Maxwell equations. The second one is a little more laborious. Here I've written it in a rather condensed form. What I mean by a vector in denominator, this derivative is really, this is a set of three equations. You have to replace a sub x here, here, and here, a sub y here, 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 a sub z. So you get three equations, each with each a. So this is a kind of sloppy notation. I apologize if it creates some confusion. So this can actually be shown to result in this equation where you see immediately that I have the curl of the magnetic field equals to the derivative with respect to time of the electric field, which is the last equation, Maxwell equation. So indeed, this Lagrangian density gives me Maxwell's equations. So now I can start, and here you see that we're following really the strict canonical quantization procedure, the Lagrangian formulation. Now I define canonically conjugated momenta to the vector potential, to the canonical conjugate, canonical coordinates. And then having done that, I can write the Hamiltonian density. This is the PQ dot minus L that we have in conventional classical mechanics. It's a little laborious here. We get, after some manipulation, this expression, which still looks strange. This term in particular looks very strange. If I integrate it, though, I can ignore it, because if I integrate it to get the total Hamiltonian at the edge of my infinite volume, when I go to an infinite volume integration, this disappears as long as I assume that the potential goes to 0 as I go to infinity. And then this term disappears upon integration. And then I had that the Hamiltonian has a promising form. Well, promising because the way we chose the Lagrangian density, it's sort of the sum of the squares of a p and of these additional coordinates here. So it looks more or less like something that I want, something that approximates a harmonic oscillator. So let's formalize it a little bit better. So exactly as we did for electrons, I take these canonical fields, A and P, and I look at the Fourier components of their Fourier components. The additional complication, so this will be just the equivalent of the C K that I had for electrons that depend on T. The problem is that these are vectors, so exactly as I did with phonons, I have to introduce polarization vectors. So I can have two different states of polarization of light, and I call it lambda. Okay, so EK lambda is just a polarization vector, and this is what will become the canonical coordinate eventually. So if I plug this into my Hamiltonian, again, I have to keep using the fact that these plane waves, these e to the kr, are orthogonal for k and k prime different. So they give me delta functions, and this permits a significant simplification of this integral. All the cross terms disappear because of the orthogonality of the plane waves. And at the end, I get that the Hamiltonian can be written as, again, a form which is promising. The square, okay, is that square of the complex number, these in principle are complex functions of time, the square of p and the square of q, which I can interpret as a generalized momentum and generalized position operators, or canonical coordinate for the field. So now we impose that these guys obey the canonical commutation rules. The polarization implies that the spin of the photons is 1, because I have two states of polarization. So it's an integer spin, so the photons have to obey Bose-Einstein statistics. So this will be the canonical commutation rules, unlike electrons. I can write the Hamilton equation of motion and see what I get. And having done that, I will not go through the details here. They're pretty trivial. I hope that you can work with the machinery here. For example, how do I compute this commutator? Notice that the Hamiltonian has this expression. So when I do the commutator, I have to plug the Hamiltonian here. The only thing that will appear in a commutator are these terms. But the term in which the Q has a commutator with the Q that I have here, they're all 0 because of the canonical commutation rules that I didn't write down, but the QQ and the PP, they all commute. So I'm left only with a commutator of the Q with a P dagger. I know what this is because of the canonical commutation rules. So I can cut my machinery and I find that the time derivative of the Q for a given K of lambda is equal to P divided by epsilon. Oh boy, some alert here. Okay. So I can work exactly the same way with a P dagger, a P dot, except that now the only term which survives is the term with the Q. The P and the P commute, so I only have the commutator with the Q, and I get this expression. So now I have that the Q dot is equal to the P divided by epsilon. The P dot is equal to the Q. So what I can do is take the second derivative of one of the two. Let's take the second derivative of this. So the second derivative with respect to time of Q is equal to the first derivative of P divided by epsilon. But the first derivative of P, I can use it from here. And so I get an harmonic equation for the Q dot, for the Q, and similarly for the P. So the Q and the P have solutions which are harmonic oscillators. So I can use the coefficient, can define this coefficient A, okay, and lambda in terms of time oscillations, harmonic oscillations of the field. It's not a surprise. I think you know the plane waves are electromagnetic waves are just oscillating plane waves. So they go like this in time. And omega is Kc, which is the usual dispersion of light, right? Where c is the speed of light. So having found out this, then I can now find that indeed these operators satisfy almost the canonical commutation rules that I want for the creation and annihilation operators. The problem is this coefficient. Notice that this is h bar divided by 2 times the frequency, the omega. I will go back to what we had for phonons. It's something similar. It's h bar divided by twice the frequency. So there is a similarity, right? The difference between phonons and photons is not just the n over and the t, but it's deeper than that. So it's almost what I want, except that there is the scale factor. Again, the same scale factor that tells me what is the field which is associated with a single photon, as we'll see in a moment. So instead of using these, let me renormalize them. So instead of using these variables here, let me divide them by this coefficient account this coefficient to divide these objects. So this essentially will convert these canonical commutation rules in which I have this unwelcome scale factor here. If I use this coefficient instead, this factor has been already absorbed somewhere else. And so the canonical commutation rules between these Lilays, which is the annihilation and the creation operator for a photon of wave vector k and polarization lambda, will be given by the usual one. So if I plug now this expression into the Hamiltonian, I get the usual collection of harmonic oscillators, each one of frequency omega k given by kc, and these are the creation annihilation operators. And there is this usual 1/2, whether you want to keep it, whether you want to renormalize it out by taking at the zero energy, whether you want to go and take, rather than this form of the Hamiltonian, where am I? A symmetrized form, if I write it as P star P and Q star Q, there's no ambiguity. If I convert this as P dagger P and Q dagger Q by second quantizing it, then the order in which I do it matters, because they may not commute. So I can symmetrize, for example, this expression by taking, rather than P dagger P, can take 1/2 of P dagger P plus P dagger. In this case, the 1/2 will change, of course, or I can use the opposite convention, and then this will become a minus. So Professor Ruda last time asked me this question, whether you can normalize it. You have to trick it somehow, no matter what you do, in my view. Okay, if there are no questions about this, we're done. I would like to take a break because I need to drink something. I'm running out of voice, and take a 5 minutes break. And so let's say we'll meet at 22. Okay, 20 minutes to whatever time is it for you. Good. Am I online? Are we good with that? Do I still exist?
Yes, you exist.
Good. Yes. Okay. I'm wondering. Okay, so let's take a little break, and 20 minutes to whatever it is, 7 o'clock, 6 o'clock for you? 6 o'clock, right? Okay, ready to resume? Should I start?
Yes, please.
Good. Okay. So, I don't know how many times I've already said that the canonical commutation rules or anti-commutation rules are very important because they set the scale of the system. Here I summarize what we can get for the electric and magnetic field, having done our second quantization, expressing the fields in terms of the creation annihilation operators. We have to retrace our steps back. So we define this coefficient A, which in terms are defined in terms of the Q and the P, the little q and the P, which in terms are defined in terms of the big A, which in turns somewhere else have been used to define the potentials and the canonical conjugated momentum associated to the vector potential. And finally, I think we are at the end of the road, we've used the expression here of the electric field and the magnetic field in terms of the vector potential. And the scalar potential is irrelevant in what we did so far, essentially because of this equation. So if we go all the way back and retrace our steps, and finally, and it is a little bit of algebra here, we re-express the magnetic and the electric field in terms of the creation annihilation operators, we have these expressions. They're Fourier components, Fourier things. Notice that this is the polarization vector for the electric field. Clearly, the magnetic field is perpendicular to it and perpendicular to the propagation. They're transverse waves. They're both perpendicular to K. And these are essentially quantities, C quantities, complex quantities with magnitude 1. These satisfy the canonical commutation rules that tells you that these are actually 1, so to speak, in terms of their magnitude. So the strength of the fields is given by these factors that we have, which is the h bar divided by twice the frequency, and then for the magnetic field and electric field we have some epsilon and mu's floating around, the dielectric and magnetic permittivity of vacuum, which of course are related to the speed of light. And so this sets the scale of the problem that we have. So if we want to calculate what is the electric field or the magnetic field associated to a particular photon of polarization lambda and wave vector k, we get the answer knowing what this factor is. We did this for plasmons, but we can go back and do it for the phonons as well, doing exactly the same procedure, following the same procedure to express the displacement of ion gamma in cell eta when a phonon of branch eta is present of wave vector q, then we can tell what is the displacement of this ion in centimeters, in meters, in whatever, when this phonon is around. Recall the classical calculation that we did in the case of plasmons. I'll review it here. What we do is we assume that we are at thermal equilibrium, and first we calculate the potential associated with a plasmon of momentum q. There was no polarization in that case. You can replace the electric field here, the square the electric field. You can replace the displacement operators over here. You get exactly the same expression because the commutation rules for the creation and annihilation operators, whether we call them A, B, C, whatever we call them, are the same. And we find out that the expectation value of the potential of the electric field or the ionic displacement when there is on an eigenstate, on a state of Fock space in which we have n, little n, excitations, plasmons, phonons, photons, it's given by this expression. This will be replaced in our two cases that I showed before by the what's inside the square parentheses, the parentheses in this expression. This was what we got for plasmons instead. A little bit different. And there is this fact 1 plus twice the number that we have here, the number of excitations that we have at that particular wave vector. We should add the eta or lambda if we're talking of, phonons or photons. Sorry, the wrong way here. Okay, so the expectation value, the thermal expectation value of the square root of the potential or the displacement of the electric field will be that factor that we have, square root, times this number. I will tell you a little bit about some complications that we may have in one particular interesting case that I mentioned before, the two-dimensional crystals, what happens to this number. But let's assume that we don't have anything around, so the ground state energy is given by essentially 1 over q times that value that we had over there, this scale factor. So this is the, I think the most important cause, or effect, I should say, of a cause which is given by the normalization conditions set by the canonical commutation rules. Again, semi-classical, you can say, well, for the electromagnetic field, if I have one photon, I know what is the energy flux that I have associated to that electromagnetic wave. I know what is the energy of one photon. I know what is its flux. And so I can extract the electromagnetic field out of these simple considerations. That sort of works. Actually, large quantum numbers, that's correct, by Ehrenfest's theorem. But this is a rigorous way to extract the electric field due to the presence of a photon, the ionic displacement due to the presence of a phonon, and the potential associated to a plasmon, which is what I'm showing here. Notice, for example, that might be another homework problem that I will assign and see if you can solve it. You can get a rough idea about the melting point of a crystal by, for example, considering what is the thermal expectation value, the ionic displacement at a given temperature due to the presence of all phonons, and assume that melting happens when this displacement is bigger than some percentage, some fraction of the interionic distance. And you get an order of magnitude estimate. Clearly, you have to be a little more, you have to do a little more work, quite a bit more work, in order to find the correct melting temperature. I'm not sure actually you can predict it out of first principles calculations, but it gives you an idea about what material will have a higher melting point and which material will have a lower melting point by considering this sort of calculations. I told you also in the past that you can follow a semi-classical calculation to find the same result. Okay, so one particular interesting example that it's perhaps a little bit a side issue, but it's a famous theorem which I will describe in the next slide. I'll tell you a little bit about its history. Suppose that this is not a linear chain, but it's a cross-section of a two-dimensional material, a monolayer of graphene or whatever you have, transition metal decalcogenides, whatever it is. Notice that in 3 dimensions, we found that the dispersion of the acoustic phonons is linear, and the proportionality constant in the sound velocity, because we solved essentially the equation of motion of a harmonic oscillator. And the spring constant was a constant. It's a fixed number that tells you what is the force constant that you have between the 2 ions, and the force is just proportional to these force constants multiplied by the deviations of the displacement from the equilibrium position, the pendulum, the harmonic oscillator. If we consider a two-dimensional material and we consider phonons which are acoustic phonons out of plane, what are usually called flexural modes, you see that the force constant now is a strange object. It's essentially the projection of the force constant that you have in plane. Since you're out of plane, you multiply by the tangent of the angle that you have when you move this red ion up. You get an angle alpha, And the force constant, which is pulling back the ion, is not a constant anymore. It depends on the angle. And the angle gets smaller and smaller, so the tangent becomes proportional to the angle and gets smaller and smaller as the wavelength increases. If I increase the wavelength, the displacement, the vertical displacement of this ion will be smaller and smaller, going from one ion to the next, from one cell to the next. So the force constant is not a constant. This would be the case if we had another ion up here, so a three-dimensional ball crystal, which is pushing and pulling this red ion here. But since we don't have it, we have a force constant which decreases linearly with the wavelengths going to infinity, or with Q, with a wave number going to zero, a wave vector going to zero. This results in a strange equation such that now the frequency, rather than being proportional to the wave vector, is proportional to the square of the wave vector. And here we have an interesting situation. Let's consider the equilibrium population, which is what I consider here, of these modes. How many do we have? This is proportional, as I wrote here, to the amplitude of, this was for the plasmons, but as I told you before, we can replace it with the displacement of the ion. So what is the thermal expectation of a displacement of the ion when you have two-dimensional phonons of this type? In 3 dimensions, there's no problem. The number of phonons that you have, this is the thermal number per unit volume, and we call omega the unit volume, is equal to the integral of this expression over the entire Brillouin zone. The problems that we will be dealing with happen at long wavelengths. So let's consider only the case, the approximation of a long wavelength behavior of this. At long wavelength, this is very small. This is very, this expression here is very small. So we are in a high temperature limit. So the exponential can be considered to be expanded in power series. And for large temperatures, we have this Bose-Einstein expectation value can be approximated by this. This is the usual elastic approximation, okay? In equipartition approximation, I'm sorry. So we can integrate this. Again, let's ignore what happens at large Q. It's a small Q that we're concerned about possible problems. So if we do the integration up to some maximum value Qmax, which is the edge of the Brillouin zone or whatever, we find an integral which is perfectly okay. And we find what is the total number of phonons that we have, which in turn tells us which is the displacement of the ion. So we multiply the total number of phonons by 2, take the square root, multiply by the prefactor that is given here, this prefactor that we have from the canonical commutation rules, and we find the total number of the total displacement that we have associated with these phonons. Okay. What happens is instead we have a parabolic dispersion and we have 2 dimensions. We're integrating in 2 dimensions. It's a problem because we're losing a Q from here. Remember, here we're doing integration over 3 dimensions, so in polar coordinates, this will be a dqq square. We lose that q square here, and we gain, sorry about that, we gain a q in the denominator because this is now a quadratic dispersion. So rather than having something proportional to q, we have lost 2 q's and place them in the denominator. We get 1 over q, which we integrate all the way to 0. And this is infinity. So the number of flexural modes that are thermally excited at any non-zero temperature, okay, not too small, otherwise we cannot use this approximation, but actually it works also at small temperature. But at some sufficiently high temperature in our simplified version here, the total number of flexural modes that are thermally excited at any finite temperature goes to infinity. So this led to what is called the Mermin-Wagner theorem. Actually, I added several names because the history of this theorem is quite interesting and long. If we go back and look at who proposed this sort of arguments originally, were actually Rudolf Powers and Lev Landau in the 30s, in the mid-30s, mid-late 30s. So I added their 2 names. Mermin, and I think Wagner was one of his students of his. So David Mermin and reformulated the problem for solid-state applications, and ultimately it was extended to a very general field theoretical framework by Steve Coleman in 1973. But the idea is of the Mermin-Wagner theorem. Actually, Hohenberg also did something. I see here, I forgot his name. I should add his name as well. The idea is that two-dimensional crystals should not exist. Essentially, there are so many of these flexural modes which at any non-zero temperature are excited that the displacement of the ions away from their equilibrium position diverges, goes to infinity. So the crystal falls apart. The fancy formulation, field theoretical, is that if you have a two-dimensional system and you break a continuous symmetry, how do you break it? In a crystal, the symmetry is not continuous anymore. You have point group symmetry, so it's a discrete symmetry, rotational, translational, whatever. So the breaking of a continuous symmetry is forbidden in a number of dimensions which is equal to 2 or fewer, because you have the emergence of, this is funny, it's related to the Higgs particles, if you want, they're called Goldstone particles in this type. You get something which is massive. Indeed, a square displacement implies that the phonons are sort of massive, that they have a mass, because the parabolic dispersion is typical of particles with mass. So if you want to put it in very fancy terms, what the simple argument says is that you cannot have a discrete symmetry in fewer than 2 dimensions because it's broken. Otherwise, you would have a divergence of the ground state energy of the system due to the presence of these Higgs particles or Goldstone particles, which are created by the symmetry breaking. So this is a consideration that has actually been addressed in a very first paper by Gaiman and Novozanov on graphene. I think it was called The Rise of Graphene, in which they said, well, it's kind of a surprise that two-dimensional crystals exist. It's a long story of why they can be stabilized or non-stabilized. In general, the early solution of the problem was, well, actually, if you look at graphene, it wrinkles. And let me tell you first something that it's an interesting story that Mermin wrote in a paper. It says two-dimensional, infinite two-dimensional crystals do not exist. Infinite. What is the critical dimension beyond which such a disruption would occur? I think he used the terms like astronomical dimensions. So in practice, they may exist. If you consider the finite systems, then the fact that you have edges and terminations invalidate the theoretical formulation of the problem. Essentially, what I would have to do here is do an integration over the minimum Q that I can have, which is roughly inversely proportional to the size of the sample that I have, the size of the crystal. So I would not have a singularity, although the number may be quite large. It may be beyond the displacement that you have for melting. So it's not terribly clear what it is. The fact that you have grains, that you have defects, that you have wrinkles, that of course you have grains, and so you have grain boundaries, which you have ideal crystal, which are only of a finite domain. They put a cutoff to the longer wavelength, the minimum Q that you have in this integration. Actually, there are other issues in many cases. I think graphene has been, you can exfoliate it and you can have it as freestanding in grains, it wrinkles, because it shows defects. But the main thing is typically when people study these crystals, they are supported. You put them on something, typically silicon dioxide, some other insulators. Often they are clamped also by a gate insulator when you build transistors, field effect transistors out of say transition metal decalcogenides. So actually one can show that there is a coupling of these flexural modes with the acoustic waves, surface modes, which are called Rayleigh modes of the substrate. Or if you have clamping, actually the square dependence on Q is essentially cut off by a finite frequency. I'm sorry about my clock. A finite frequency, and we have 11 of them now. which is caused by, you can use an elastic continuum. I didn't put a reference here. There are several papers in which they discuss the fact that you can regularize somehow the dispersion of the phonons. Here it shows actually some experimental value, which they show that the hybridization with the Rayleigh waves of the substrate can give, essentially you linearize it. Rather than having a square dependence, you can actually linearize it. This is actually not true for graphene. For graphene, you need something else. Graphene has a van der Waals interaction, so there is a gap, a van der Waals gap, and the clamping that you get from purely van der Waals materials is not strong enough. Actually, in this paper, it actually happened to be by a former postdoc of mine, a student of Eric Pops at Stanford University, and they actually had to increase by about a factor of 10 the strength of the van der Waals interaction in order to linearize the dispersion. If you linearize it, then at least you lose this Q and you get something finite. You don't have a Q square over here, you just have a Q. This, of course, works in all conditions, and it's an interesting problem. And maybe in the future I will mention a little bit how this affects electron transport. The good thing is that electrons do not couple with these modes if the material that you're dealing with is symmetric under reflections on the plane, like graphene. Graphene is perfectly symmetric. If you look in a mirror, you see exactly the same thing. Transition metal dechalcogenides, which have a hexagonal structure, they are also symmetric. And the first order interaction between the electrons and these phonons is forbidden, so it's good. For materials which are not symmetric, and there are several, like tetragonal TMDs, buckled materials like silicene, phosphorine, when it's buckled in a bad way, they're not symmetric, and then there are some issues which are an interesting problem that people are still studying. So just a curiosity of what kind of considerations you can derive from this sort of things, and you can do the calculation thanks again to the canonical commutation rules, because they can tell you the scale. So again, I will post an homework assignment in which I will ask you to calculate the melting temperature of a hypothetical crystal, maybe silicon, considering some phonons, and see if you get in the ballpark of the order of 1000 Kelvin. I don't think you can do much better than that. There are some rules about what is the maximum displacement, ionic displacement that you can have away from thermal equilibrium before anharmonic interactions begin to be strong enough, and you approach melting. So this is a typical example of what the canonical commutation rules can give you. So totally different topic now. Any questions about what I've said so far before we go into this new topic? Nope. Okay, so we will be dealing with electron transport eventually. We'll get there, I promise. So electrons move in a crystal. I think I mentioned it actually by when we talked about the block oscillations. An electron in a crystal that doesn't interact with anything. In an ideal crystal at zero temperature, it doesn't even emit phonons, so in a very idealized and realistic scenario, would not conduct current. It would just oscillate according to the block oscillations. So electrons interact, and actually their interactions with elementary excitations, it's very important. Essentially, it's something that you cannot avoid. Interactions with defects, with impurities, with interfaces, in principle, you can avoid it in some cases. With interfaces, you cannot, if you're building a device in which you need interfaces. But impurities, defects, you can try and minimize their effect. Nowadays, channels are mostly undoped. So in principle, you could, to avoid doping fluctuations and fluctuations of the threshold voltage or turn-on voltage of the device caused by the fact that you have so few dopants, so people avoid doping them. But interaction with elementary excitations are crucial, and you cannot avoid them. And don't mean just interaction with phonons. Of course, you can always have them. Even at zero temperature, you have spontaneous emission. So you can emit phonons if the electron energy is sufficiently enough to emit them. Also, electron-electron interaction. Electron-electron interaction, we will discuss it, can be split into a long range and a short range interaction. A short range, we have excuse me, fluctuations of the Hartree potential. The Hartree potential assumes a mean field, static, and electron fills the field of all of the other electrons. Actually, the other electrons move around. There are density fluctuations. And at short range, this causes single particle interactions. At long range, this causes interaction with plasmons, which affects the electron distribution functions, although it doesn't affect the current directly. In magnetic materials, you have interactions of the spin that the electron have with spin waves or magnons, magnetic excitations, which are quantized the same way we have quantized so far a bunch of other fields. These are viewed as perturbation of the crystal, and the electrons interact with them. However, if you consider an electron which is moving in the conduction band, even in an intrinsic material, if you have injected this electron somehow, valence electrons are still there. The ions are still there. So other charges are around, and they can affect the perturbation by changing the potential. If you have another electron, the ions can polarize and can screen that electron. The valence electrons can do the same by moving away from the other electron. For impurity scattering, it's the same thing. You have a charge impurity, and the valence electrons screen it. Of course, this is reflected in a dielectric constant, but we have to get there rigorously. So in general, other charges, including other free carriers that you have, if you have a doped semiconductor, or if you have a channel in which you have a gate bias which has induced an electron density, these electrons are free to move and they respond to the external perturbation. So the idea now is to look at how a crystal, the ions, the valence electrons, and free electrons respond to an external perturbation. The procedure that we follow is the usual procedure that you get in linear response. As engineers, you will see many examples of what we may call a transverse function. So you have a system, which is your black box, and you have some time-dependent waveform, a perturbation, a voltage, a current, an electric field, whatever you have. Somebody with a hammer, which is giving a mechanical perturbation. What we do is we decompose the external perturbation, the input waveform, into Fourier components in space and time. And we analyze one Fourier component at the time, assuming that they don't mix. It's what in general we will call the random phase approximation, an RPA. If you perturb the system at a given frequency, spatial or temporal, the system will respond at the same frequency. Of course, there are exceptions to these rules, no linear crystals, optical crystals, for example. But except for a few interesting but pathological cases, and as long as the perturbation is weak, such a coupling can be ignored. And we will talk about it in some detail later on. So what we assume is that there is a system that is black box, responds somehow, and we characterize the, actually I swapped the in and out here, my apologies, in and out are to be swapped. The output wave function will be given by the input waveform, whatever perturbation it is, times a function, which is different in principle for a given wavelength, for a given frequency. Okay, so I apologize for having swapped the subscripts over here. So this is what a linear response consists of. And this can be an electrical circuit. In our case, it will be a crystal, and this external perturbation will be typically a potential, an electromagnetic wave or some bias, time-dependent bias that I apply to my device, some dependent voltage to a contact, and I see what happens to this crystal. Now, so in our case, the input will be some external potential that we apply. The output potential will be a total potential, which will be the sum of the potential that we apply plus the polarization of the system. When I apply an electric field, the system will polarize. Let me give you a typical example. This is water. I have a capacitor, two plates, the left and the right, and there is some dielectric, let me say water in between. Water is HO2 molecules, so you have two H's which are positively charged because they have transferred significant part of their electron to the oxygen, and oxygen which is negatively charged. If I apply a positive bias on the left plate, what will happen is that the oxygen which is negative will try and move towards the positive plate. So essentially this H2 molecule, which can view as the head of Mickey Mouse with the two ears, which are the hydrogens, and the head, which is the oxygen, the head will move towards the positive bias, and the ears of Mickey Mouse will move towards the negative bias. It rotates. It can rotate. It can also distort. Once it has rotated, the electric field, let's assume it's low frequency, so it's very slow varying in time. You can distort by moving the charge. You had a transfer of electrons from the hydrogen to the oxygen. You can increase or decrease this transfer depending on the sign of the field which is applied. So the system can respond. This rotation of the molecules or polarization of the molecules causes a dipole. The dipole induces a field which adds to the field that I'm applying externally. So the total potential will be the sum of the potential that I apply externally and the polarization. The response of the system, it's something that we will call the dielectric function of the system, which in Gaussian units is just the polarization of the vacuum permittivity, 1 in Gaussian units, epsilon 0 in SI units, plus something that we call the susceptibility, the electric susceptibility of the system. And the electric susceptibility is caused by two factors, the ionic polarizability, which again is a orientation of the molecules in a liquid. In a crystal, you don't rotate them, but they can polarize. Clearly, you can have charge transfer because the ions move. The valence electrons can move, so there is an electronic response. And if you have free electrons, the free electrons respond as well. I show here a result of what we will be finding eventually. This is the frequency of the external perturbation that I apply, and this is the dielectric function. I apologize if sometimes I will talk about dielectric constant when indeed it's a function of Q and omega, it's a function of everything. You understand that this function, this response to the system is a function of frequency. For example, coming back to the example of water, I apply an electric field which is varying in time. So this left plate can have a voltage which goes from positive to negative, and so on. So it oscillates. Clearly, in order for the system to respond, the water molecules here have to rotate. It takes time for them to rotate. So if the time that it takes for the field to swap from positive to negative is very long compared to the time it takes for the molecule to rotate, then good, I will have a strong effect, a strong polarizability, ionic polarizability. There will be a full response, and this is what we may call the static response, the static dielectric constant. If I begin to increase the frequency, I may reach a point in which the molecules do not have the time to rotate. If it takes some time for them to rotate and the field is swapped from positive to negative in a time which is shorter than the time it takes to rotate, which is given by the moment of inertia of the molecules, of course, then the response will begin to drop. So from a full response to the system will begin to drop. Here I call it boundary because of boundary effects, but it's not what really I mean here. But it will drop. At some point, after I've stopped with this possible rotation or polarization due to the rotation of the molecules, so my dielectric constant drops from some value to another value. We'll talk about this up and down swing later on. I may reach another value in which now the electrons can begin to polarize inside the molecule. Again, it takes time, much shorter than the rotation of the molecule. So the ionic response will be much slower than the electronic response. But at some point, I will reach a frequency in which the signal changes from positive to negative in a time which is shorter even than the time for takes the electrons to polarize. And then I go back to some lower value. And eventually I may have, if I have free electrons, clearly an example of water, it doesn't apply, but if this is a crystal, I may have conduction electrons, conduction holes, depending on how it is doped, if I've doped it. I have valence electrons. So at some point, I will be left over only with a polarization, say, of the valence electrons. By the way, the time response of the of electrons in the valence on conduction is given by this plasma frequency. You remember that the plasma frequency increases with the square root of the density. So conduction electrons, in which might have densities going from 10 to the 15th to maybe 10 to the 21st per cubic centimeter, will have some plasma frequency, which is of the order of millivolts to hundreds, maybe 200 millivolts at realistic densities. Valence electrons instead have densities of 10 to the 22nd, 10 to the 23rd, depending on the material. So they have plasma frequencies which are of the order of EV to tens of electron volts. So the last thing that stops responding will be the valence electrons at frequencies which are way above what is of interest. And I mean, you're beginning to be in the gamma rays at these frequencies. X-rays for sure. So the general feature that we will see is that the ionic polarizability will be large at low frequencies. Then we will go through some transitions when some ions stop responding or some phonons stop responding. We may have more than one phonon, and then we will have different up and down swings that are essentially due to the what is called the oscillator strength or the F strength of the phonon, which tells you how much the polarizability of the crystal depends on one particular phonon. Again, optical phonons are dipoles, so as long as they respond, they affect the polarizability. And eventually we will be left with a dynamic polarizability or optical polarizability in which only the electronic response is still occurring. The ions do not respond anymore. Eventually, very high frequency will recover the frequency of vacuum when we are in tera-electron volts and milli-electron volts range. So in general, what we will have to do is consider separately the ionic response to an external perturbation and the electronic response to an external perturbation. And we'll deal with them separately in the following. Okay. In general, just to set the frame for what we're going to do, we will use electrostatics. In principle, we should use Maxwell equation. Even for phonons and interfacial excitations and so on, it's good enough. It's very rare that you see people dealing with retardation effects. The same way when we talk about optical transitions in a solid, we say that they are vertical transitions. So there's no momentum exchange. There is, but the momentum is so small compared to the other wave vectors that you have in the system, the size of the Brillouin zone, that we can ignore it. In other words, we can consider the speed of light infinity. If we're dealing with devices, typically the delay time that you have in a device due to the propagation of light is very short for all practical applications. We are in a few femtoseconds over distances of a micron. If devices are shorter yet, clearly it's even shorter. At the circuit level, the chip level, probably many of you know better than I do, this is actually an issue. And indeed, the delay caused by the propagation of light was an issue in the old days of bipolar technology. We will be using the random phase approximation. So we have a general waveform. This is my input function here. Oops, sorry. My input function here. And we decompose it into Fourier components in space and time. And so we'll assume a linear response, and these frequencies do not mix. Okay. So what our problem will consist of will be, okay, I take one particular spatial frequency and one particular time domain frequency. I will consider the total potential, which is what I'm interested in, as the sum of the potential that I'm applying, plus the polarization potential, which is the result of the dipoles, the microscopic dipoles that are due to the displacement of the ions, the polarization of the electrons, and so on. The motion of the electrons, the plasma response of the electrons, if you wish. We will assume that this polarization potential is proportional to the total potential. Let me mention in a moment a little bit of a detail here. So, and the proportionality constant is what we call the electrical susceptibility, and it's called by the letter chi. So if I want to lump this into a unique factor expressing the total potential as a function of the external potential, and I can define a dielectric function like this. Typically, if this response is weak, it's linear, you can assume that the polarization potential is actually proportional to the external potential only. If you wish the total potential now that I use here, I should replace it recursively, right? The total potential that I use here, again, I go back here, I express it as the sum of external and polarization. The polarization I express as some external polarization, and I end up with an infinite series, which is actually a geometric series that I can sum. So typically, in a self-consistent way, what one does is define epsilon as 1 over the sum of the series, if you wish, or we solve directly epsilon, the phi external in terms of phi total by solving this equation relatively simply, right? You choose. Usually people use a non-self-consistent response by approximating this total with the external. So dropping the higher order terms of the polarization, and which is amounts to assuming the small chi limit for this expression. You can write it this way. Either way, it's up to you, whatever you decide. Sometimes people call it self-consistent RPA. Chi is not really zero, so if it's the order of a few percent, you begin to have some differences depending on whether you use the self-consistent solution of this, in which you solve for phi tot in terms of phi external, so epsilon is equal to this, or whether you use the non-self-consistent approximation. This is the usual expression for epsilon that you should have seen in electromagnetism 101. This, if I take the gradient of this, is equal to minus the gradient is the displacement field D. If I take minus the gradient of this, I get E, the electric field. So epsilon is what I have here. One has to be a little bit careful because of the gradient. If this is a position-dependent quantity, it matters as well. Before I proceed, one thing as well, coming back here, this is in terms of frequency, and I explained that this is a dependence on the time frequency. It can have a dependence also on the spatial frequency, on the wavelength. Coming back to our Mickey Mouse analogy of the water molecules, if the electric field that I apply, the perturbation, has a frequency especially very high, which also implies usually a high time frequency. But if the field changes from positive to negative over a distance, which is shorter than the size of the molecule, that molecule cannot rotate anymore. One side is pushed to rotate clockwise, the other side is pushed to rotate anti-clockwise. So it may polarize, but it will not rotate. So we will lose a portion of the response, even as a function of frequency. And we'll see that this happens actually for free electrons in dielectrics, in semiconductors. So this is the general scheme that we will use, and I will have another slide in which I will relate it to conventional definition of the dielectric constant function, whatever you want to call it. But this is the general scheme, and we will deal separately with the dielectric response, which is due to this chi, due to the ions, and then what is due to the electronic response. This is what you have in some slides that I've posted. Typically, you write the polarization in terms of fields rather than potential. It's the same thing. And whether you assume that the polarization is proportional to E or D, so the total field or just the linear approximation, here I've used the linear weak response approximation. This is the typical definition of the electric constant. If I replace E with D here, forgetting the epsilon zero that I have to rescale by, then I will get a definition which is given by this expression. It's the usual thing that you should have seen in the first introduction of what is the dielectric constant of a medium. Let's go back to the linear chain. So let's start with the ionic response. So this is the same, exactly the same slide that I showed before, except that I want to point out one fact. What we're going to calculate now is not the dispersion of the phonons that we've already done, but let's assume that I apply an electric field now, say along this direction. If this is positive, this is negative, the electric field points this way. So what I will have is that the negative ions will move one way and the positive ions will move the other way. So there will be a net dipole or a net difference in the displacement of the two ions, which is not only what we have because of the thermal excitations, the phonons, but because of the fact that we have applied an external field. So we want to find an expression for the displacement U2 minus UV1 or V1 minus V2 that we have between the two ions as a function of frequency of the electric field that I apply. In terms of a function, an expression which is linear in the electric field. And the proportionality constant will be the dielectric susceptibility chi that we want to calculate, which is due to the ionic response. So remember what we did. We wrote the equations for the eigenmodes of the system. This is just the acceleration of the ions 1. Forget which one the ions 1. Let's say the big one. Yeah, the big one because of the big mass here, which is due to the push and pull from the left and the right, and similarly for the ions 2. We use the periodicity of the crystal, as I told you before, and then we solve for the eigenvalue equation, blah, blah, blah. This is what we obtained. And I remind you that we obtain optical phonons and acoustic phonons. Okay, now let's do something different. Now let's apply an electric field, and let's assume that this electric field is a constant spatially, but it changes in time, sinusoidally, according to this rule. So now my equation of motion that I wrote here will be the same, sorry about that, over here, but I have to apply the electric field, okay, at a given frequency. So if I solve the equation of motion, now I have the usual push and pull of the electrons from the left and the right, the ions from the left and the right, but I have also the effect of the electric field. I'm assuming that one ion is positive, one other ion is negative, and that's why there is a sign difference of the force, the acceleration that the electron feels. If we subtract divide by m the first one and big M the first equation, little m the second equation, and subtract them, we get an expression which is what we wanted for the V2 minus V1, which is the relative displacement of the two ions in terms of a proportionality constant times the field. This mu is the reduced mass of the two ions. Now notice that this is just the frequency, square frequency of the transverse optical phonon. It is exactly this guy, right? It's exactly this guy at the zone center. This frequency here. So this is the frequency of the transverse optical phonon at the zone center. So we can write the displacement as a function of frequency as some constant in front here, which is proportional to the electric field, E divided by the reduced mass, and then omega TO square minus omega square. Here is recognize the resonance. This is the harmonic oscillator. That's what it is. It's my phonon, and I'm exciting it with a force which has a frequency, which is different from the eigenfrequency omega naught, which is this omega TO of the system. And clearly, when I excite the system at the resonant frequency, I get an infinity for this object. So usually, in a realistic situation, there will be a lifetime. Phonons decay, all the terms which are higher order in the displacement beyond the square of the displacement will be called the harmonic terms, will begin to enter the picture. Phonons can decay, optical phonons can decay into acoustic phonons, the anharmonic interactions. If there are electrons around, phonons can interact with electrons, so they have a lifetime. A lifetime means that this object actually will have an imaginary part. And so this, rather than being a singularity, or as I said, will take the shape of a Lorentzian, or the real part of this will take the shape of a Lorentzian. The imaginary part, as I mentioned in a moment, will contribute to the attenuation of these electromagnetic waves that I'm shining on my system. So what is the polarization? The polarization field due to these guys will be just the charge times this displacement. And then, of course, I have to multiply by the number of dipoles that I have per unit length, the number of phonons that I have, the number of ions, sorry, that I have. So I can write the polarization as the electric field times this, which is my chi. This is nothing but the dielectric susceptibility of the system due to the response of this particular optical phonon. Notice that now I have to specify the dielectric constant, whether it's static or the infinity here means at the frequency which is much larger than the frequency, this frequency, the eigenfrequency of the system. Infinity will mean something different depending whether we're dealing with electrons or with ions. It's a frequency in which the system does not respond anymore. So for ions, it will be a smaller frequency than for electrons. This prefactor in front of the resonance with a TO, like usually I can multiply by the TO in front, so I get the frequency dependence qualitatively normalized to a peak of 1. When omega is equal 0, I get unity. There is a resonance, a peak here. Clearly, it will reduce to a Lorentzian if I assume that the phonon has the lifetime, so there is a line width for the phonons. And this is just the prefactor in front of this is just the difference between the electric function when the ion responds and when the ions do not respond. So by definition, I can write it in this way, and this is what is called the F strength or oscillator strength of the phonon. It's how much this particular phonon contributes to the polarizability of the medium once I perturb the system at a particular frequency. This is in a long wavelength limit. At short wavelength, I will have to deal with more complicated effects, and it's not extremely important. The frequency dependence, the spatial frequency dependence is not particularly strong. It begins to be very important only at values of the wavelengths which are extremely short, and typically we will not have to deal with that. So usually the small Q limit is a good approximation. So this is how we can write the electric function as a function of frequency only. We have to interpret Q approximately 0 here, due only to the ions. It will be this epsilon infinity, which is, I apologize for this, will be the 1 that I wrote here, if you wish. It's this 1. In SI units, this becomes epsilon 0, or in our case, we haven't dealt yet with electrons, so this will be the static dielectric function due to the electrons, whatever. So there is this factor of, let's call it 1 for now, and then there is the deviation from the static the polarizability when the system does not respond. So the increase in the response or the polarizability of the system caused by this phonon, which goes through a singularity. I can rewrite it this way, okay, in this particular fashion. If we consider the frequency, and that is something that we will have to discuss later on, the 0 of this function as the frequency of the longitudinal optical phonon, which we will discuss, why that is a general property. When this is 0, clearly I can write this polynomial in omega square, except for this prefactor, that is the denominator that I pulled out. I can write it in this fashion by usual algebraic rules. So I can rewrite it in this particular fashion. This is useful because it shows that there is a region of frequencies in which the dielectric function is negative. And that happens when omega is between the TO and the LO frequency. The LO frequency is always bigger. We will talk about this. What does a negative dielectric function mean? It means that an electromagnetic wave will be attenuated. It does not propagate. I remind you that the K vector of an electromagnetic wave is given by this dispersion, the dispersion omega In vacuum, it's clearly epsilon is epsilon 0, it cancels out, and we recover omega equals ck. But in a medium, characterized by the electric constant epsilon 0, you realize that this thing is actually 1 over the square of the refractive index of the medium. So if we have a negative dielectric function, or a region in which the dielectric function is negative, this means that the dielectric index has an imaginary part. An imaginary part means that the plane wave, which propagates, is e to the I kx. And this k will have an imaginary component, and this imaginary component corresponds to an exponential damping of this. So in the region, which is the transverse longitudinal optical phonon gap, in that region, which is essentially what I illustrated here, in this region here, actually, if we don't assume, as I've assumed in this plot, that there is a finite lifetime for the photon, this will shoot up to plus infinity and will shoot down to minus infinity. It is in the region in which this is negative, which is the TOLO gap, that electromagnetic waves are attenuated. And they interact with the transverse optical phonons, actually. I told you, if I set this equal to 0, I find the frequency of the longitudinal optical phonon. This is a general property. The zeros of the dielectric function, this is something that you should keep in mind. It's very important. The zeros of the dielectric function are the longitudinal excitation of a medium. Why is that? Suppose that I have an electromagnetic wave propagating. I consider only the electric field here. It's given by some fixed value E naught for the field, and then there is the usual plane wave propagation. Now, if I talk about eigenmodes of the system, there's no external charge in the system, so the divergence of the displacement field D has to be equal to 0. For a particular frequency, this can be written as epsilon times the divergence of E. Now, there are two ways in which this can happen. If this is a transverse wave, the k vector is perpendicular to the E naught. So if I take the divergence, I get k dot E naught. For a transverse wave, this is 0. So this is always true. Actually, we will see, and we see already from this expression, that the transverse mode, the transverse phonon, actually is a pole of this, is an infinity of the dielectric function. If the propagation, the electromagnetic wave that I consider is a longitudinal, then k dot E naught is equal to a non-zero term, which is essentially the magnitude of k times the magnitude of E naught. So this is not 0. So I must have epsilon equals 0. And this defines the frequencies of the longitudinal mode that I have. Okay. One interesting thing to notice, well, there are two interesting things. First, since D is equal to epsilon E, if epsilon is 0, you can see that the displacement field D, which has to be 0, can actually be associated with internal microscopic electric field, which is not 0. And that's why electrons cannot couple to transverse modes, because the field is 0, but the field of longitudinal modes, the microscopic field induced by the eigenmode, will be non-zero, can be non-zero. And so electrons can couple only to longitudinal modes, with the caveat that I told you before, that in reality there are no pure longitudinal modes, no pure transverse modes, but in general the coupling with the transverse mode goes to 0, the coupling to the purely longitudinal modes is non-zero. The other thing is a very important relationship between the frequency of the longitudinal optical phonon and the transverse phonon. If we go and look at this particular way, this again is a consequence of the fact that I've written this as a polynomial divided by omega t squared minus omega squared. The polynomial that I have here has to be 0 at the omega LO, so I can write it this way. And this is the constant of proportionality that I need. Okay, if I write it this way, I see immediately that I get the omega LO frequency is related to the frequency of the TO by the square root of the ratio of the static over the optical dielectric function. By the way, the large frequency dielectric constant sometimes is called optical, because that's the high range of frequencies in which optical light lives. This is called the Ledane-Sachs-Teller relationship. Okay, it's an important relationship. Clearly, the static dielectric constant is bigger than the dynamic. This is bigger than 1. Therefore, the TO frequency is always larger than the phonons in silicon somewhere. Okay, here it is. Actually, the LO frequency is always bigger than the TO. Okay. That's the consequence of this LDS relationship. It's never so simple, unfortunately. Life is complicated. In most materials, you have more than one phonon, except for, say, diatomic material, which you have two. So not diatomic material, which two atoms per unit cell. You may have more than one optical phonon, and then things get more complicated. And typically, the dielectric function will be written by this epsilon infinity plus one term per phonon that you have, and this will be related to the contribution to the change of the electric function that each phonon does. So this is the net result of our, from the final result, either in this way or in this way. They are equivalent if you have only one phonon. If you have more than one phonon, they're not really equivalent. One has to be a little bit careful in some situations. But this is the usual approximation that is made to approximate the ionic dielectric response of the crystal. Any questions so far? No? Good. Okay, calculating this thing is a different story. It's, of course, by definition, is equal to this, to the difference between the epsilon 0 and epsilon infinity. Calculating it, it's always a little bit more laborious than what I've written here. Simply written here in simpler terms, but this is a little simplified model. But still, this is correct in the long wavelength limit. Okay, let me just conclude this class by telling you what is the strategy that we're going to follow to calculate the electronic response. So I told you before, response of the system is due to what the ions do, and we've calculated that, what the electrons do. And electrons, we have valence electrons, which of course are very important. After all, they fix the electric constant to the material, and free electrons that may contribute as well. So there are many ways to solve this problem. In many textbooks, people use Green's functions. That's good. I don't have any problem with that. I prefer a more direct method to calculate the electronic response. The more direct method is the following. So I have this expression. This is the same that we used here. Okay. I want to calculate the total potential as the sum of an external potential plus the polarization potential. Okay. So that's the potential that essentially contributes to scattering. It's what the electron will feel if I have any time-dependent perturbation given by some potential, like those due to a phonon, that we will calculate in due time. So phi external is a bare potential in some sense, and this is what we want to calculate. So we have to calculate that. Again, we're going to use the random phase approximation. So what we will do is we will write both the external perturbation as well as the polarization charge, and so the polarization potential, in terms of Fourier components for a given Q. I didn't write the omega here. In principle, I should write the omega, and the epsilon indeed contains the omega. This is a shorthand, but everything depends on omega as well, these Fourier coefficients. And then we will calculate the external perturbation actually as the difference between the total potential and the polarization. So just reverting the equation that I showed before. And this gives us for a given frequency Q and omega, it gives us the external potential in terms of the Fourier component of the total potential, so that we can reverse it, if you wish, in this expression. This little r means relative. There's the usual thing that using SI units, the permittivity of vacuum is not 1, it's epsilon 0, so it complicates the notation a little bit. So for now, I will write the relation between these two as 1 minus the ratio between the polarization potential and the total potential. So this is the equation that we want to use. I manipulated a little bit my definitions. So what we have to calculate in order to calculate this, which is this relative dielectric function, which is just the dielectric function if I use Gaussian units, I need to calculate the Fourier components for a given Q and omega of the polarization potential. And in order to do that, I will calculate the Fourier components of the charge which is caused by the external potential. Okay. How do I calculate this charge? I will use perturbation theory. Essentially, I know what a wave function is in terms of the unperturbed wave function. These are the block wave functions of my crystal, okay? Which in a bracket notation I can write as K mu. Mu is a band index. Which band I'm using? K is the block K vector projected over eigenstates of the position operator at time t. This is just a bracket convention to write my wave function, my block wave function. I know what they are. So I want to calculate the total wave function in the presence of the perturbation in terms of the known wave functions and of the potential, of course. So I will use first order perturbation theory to calculate the correction, the first order correction of to psi, so of phi, of this perturbed wave function in terms of the external perturbation. So I will write phi as the unperturbed block wave function plus some change, and this change is written in terms of first order perturbation theory. It is a sum over all of the block function, unperturbed wave function, with a coefficient which has a numerator, the matrix element of my perturbation, which is E phi, and in the denominator, the energy difference between the perturbed, the unperturbed eigenstates at K in band mu and K prime in band mu prime. So a sum over all unperturbed states, and I consider the change in the difference of the energy of the two. And there is, of course, the factor h bar omega, because the potential that I have here is supposed to be time dependent. I think I will defer to next week, a discussion of why we need this. You realize mathematically we have some problems when we integrate, we convert this into an integral, we integrate over K, where mu and mu prime are the same, and K, the integration over K prime crosses K, we have a pole of this. So it's a benignly divergent singularity. We will have to do something that can be treated with a famous theorem in complex calculus that I will review next time. Anyway, to keep for next week the details of how we're going to do these calculations, this is the general expression for the wave function. To calculate the charge, remember, I want to calculate the charge, the difference of the charge that I had between the perturbed system and the unperturbed system, which is the response, is the polarization charge, is the response of the system to the perturbation. I need to consider the square of the wave functions. Notice that I'm considering conventional quantum mechanics here for now. And then I can calculate the total charge, the total change of charge, by considering the leading order term of phi star. This will give me the Fourier components of the polarization charge, which is caused by the perturbation. Okay, so this will be the strategy that we will follow, and I can probably have a few minutes. I can proceed a little bit more. So what we have to do now is first to understand how to calculate this potential. This is a little tricky because these are block functions, so there will be a bunch of nuisance, annoying terms, sums over G vectors that we will have to deal with. If you go and look at this equation here, we have to take the matrix element between this and the block functions. For the block functions, we can use the usual expression, and we find that the matrix element of the potential, unfortunately, is not just the Fourier components of the potential at the Q vector corresponding to the difference between K and K prime. That is what we would get if we were dealing with free electrons, not in a crystal. So if these were plane waves, that would be pretty obvious. Unfortunately, we have to drag the Fourier components of this factor, which would have been just the delta function that simplified our calculations, over the block functions, which is the Fourier, the periodic components of the block function. Anyway, so now the new charge is obtained by summing over all the square wave functions for a given k by mu. I have to sum over all occupied states and all over bands the square of the wave function multiplied by the electron charge. And let's denote by P, K and mu, the occupation of a state K and mu. So the total charge due to the perturbation, so the total polarization charge, will be the sum over all occupied states of the square of their wave functions multiplied by the electric charge, the electron charge. Now, remember, we're dealing with perturbation theory. We want to retain only leading order terms of the perturbation. We don't want to go to the square of the perturbation. So the phi's are given by the psi, the unperturbed wave function plus whatever is the difference. So in order to keep only the leading term, the phi square or the psi square, which are the unperturbed terms, can be separated, and this is the charge that I had before. And then I will have two terms, which is psi d psi star and psi star d psi, which I've written as complex conjugate of this term. So this will be the sum over the charge. There is a square of the charge because I have the potential that I consider over here, which is already as an E. Then there is the occupation factor. Then there is the psi star multiplied by the delta psi, which is one of the two cross terms. And the delta psi is what we wrote over here, plus the complex conjugate. Okay. Now, we can swap. We can do a little bit of manipulation, swap the dummy indices K and K prime, expressing these things in terms of their Fourier transform, which are the block functions and so on, using this expression that I wrote over here. So we do this little manipulation, and this term only, plus the complex conjugate, which is the delta rho. I don't care about the rho zero. We want to change the change of the charge. So the rho minus rho zero. So this goes away. The delta rho, which is this term plus complex conjugate, will become simply this. Okay. Now we see that this is the delta rho expressed as a sum over Q of e to the IQR times phi Q. So we can immediately extract from here this term with the sum over the G, the mu, mu prime, and K. The sum over Q is just part of the Fourier transform. We can find that the Fourier components of the polarization charge is given by this expression. Okay. Now, having found the Fourier components of the charge, the polarization charge, I can use Poisson equation, okay, that tells me that the polarization charge is equal to epsilon 0 times the Laplacian of the polarization potential. Okay, so I can use that to find what is the polarization potential, and its Fourier component, which is 0q divided by the q square, which is what I get from the Laplacian for each Fourier components. And finally, recalling what we were up to, we're up to calculating this relative dielectric function, which is epsilon q omega divided by epsilon vacuum, will be equal to 1 minus the minus sign, which I get from here, from the expression that I had before, somewhere over here. Okay. And then this royal mess. We will deal with it next week. By the way, if you assume that this is equal to 1. This is what you would get for a free electron, and this is what is usually called the Lindart dielectric function of an electron gas. There's no sum over G, of course, because we've gotten rid of it. And there's no bands because we have only one band for a free electron gas. It would be simpler. So next time we will have to deal with how to calculate this. In general, for a degenerate system, this is not, we cannot calculate it analytically. In a non-degenerate limit, yes, it is not simple. It involves a particular function which is called the plasma dispersion function. You can find it in many textbooks. I would probably go through some brief outline of the derivation, but it will be interesting to see some particular case, in particular the static dielectric constant, when we consider only the effect due to a field valence band, mu prime, and empty conduction band, mu. Look only at what happens here. This would be the case of the electronic response for an intrinsic dielectric, an intrinsic semiconductor. So in the case of omega equals 0, which will be the static dielectric constant, the 11.7 for silicon or 16 for germanium, whatever you have. Then we will consider the case of free electrons. In a case of, so if you have a doped material, and what happens to the response of the free electrons in two different limits, small frequency, omega go to 0, as a function of Q. So the static screening, and vice versa, long Q as a function of frequency. So small Q, long wavelength, as a function of frequency, which is the plasma response. And then I'll outline what is the possible way to calculate the total dielectric response. It's kind of in closed form analytically, but then you really have to do it numerically because of the plasma dispersion function, which is only an analytic definition, an integral definition. So it's analytic, so to speak, because when you want to get numbers, you have to put it in a computer anyway. Okay, I'll stop here. Please ask questions. Any question? No?
I have a comment.
Yes, please.
I think that the circular equation was called so because it was used at the beginning to study planets, the motion of planets that takes much longer than the electrons to move.
I thought it was called like that because it took me a century to understand it, but you may be right. Yeah, that's a good point. Yes, it's probably true. I'll Google it.
Okay.
Let's see what I can come up with. Okay.
Thank you.
If there are no other questions, have a good weekend, and I'll see you next week.
Thank you.
Bye-bye.
Thank you, Max. Bye-bye.
Bye.
Alla prossima.
Thank you, Professor.
Ciao, ciao. Bye-bye.
Ciao.